but I will Shailendra. So I will give you enough flavor, enough knowledge so that you can do this kind of MATLAB JADE interactions. Okay.
Uh, Hello, sir. Am I audible?
Yes,
Yeah.
Dipayan, how are you? Good evening.
Deepak, sir. Sir, how are you, sir? Good evening, sir.
I am fine, thank you.
Sir, just a request. Can you please spare some time on frequency control by using multi-agent cells?
Frequency control. I
Yeah.
think we have a couple of slides. One of my PhD student work on it. Frequency control. Probably you might have seen our paper. We have a transaction paper on that one.
Yes,
So
sir. Yes,
we'll
sir.
talk
Yes,
about
sir.
it. Yeah, we'll spend a little bit time. I think I have a couple of slides tomorrow. Okay, Deepayan.
Okay, sir.
Okay.
And sir, just one query, sir. If you allow, then I can ask you.
Say that again.
I said that I have just one query. If you allow me, then I can ask you, sir.
Yeah, sure, sure. Go ahead, Deepan. So means nothing. I don't
Actually,
want to help. Yeah.
actually, sir, for the last discussions, what I understand is that okay, whenever we talk about the development of the multi-agent systems, we have to have a solid background of the environment. But if we talk about the voltage control, then these power systems models, if we have the frequency control structure, then the models, all these things we have to have. Now the thing is that when we talk about the mathematical modeling of a real-time systems, we always have to have some sort of modeling headers because it is not possible to include all possible entities within the mathematical models. So that's why I asked the same question yesterday also. Then how we will ensure that the control systems which we developed under the multi-agent framework will work fine, or how we are going to quantify its performance in that case,
Okay.
because
Very
at
good
the end
question.
of because at the end of the day we have to ensure the overall system stability as well as robustness of the entire control structures. So
Okay.
that's why I raised this question yesterday also, sir.
Okay. Dipayan, a lot of questions in that one. Okay. A lot of questions. Okay. So let me see
Okay,
if I can break down. Okay. So, uh, stability system level, right? When you have decentralized control, stability means transient stability. There is nothing we can do about it. We don't have time frame. Transient stability is like mostly microsecond, milliseconds, or maybe couple of seconds. That's it. Again, we don't have that much time when we do work with decentralized control. So decentralized control, from my perspective, won't be able to help in the transient stability. But dynamic stability, yes. Okay, so uh, dynamic stability, voltage stability, right? And then frequency stability, not primary, secondary frequency stability, secondary control of the frequency, secondary control of the voltage, right? So voltage stability, angle stability, and frequency stability. Okay, so that's where the decentralized control can play a good role. Okay, and now that is first question, right? Second question is that how do you ensure, right? How do you ensure, like in mathematics, that you write this optimization, and then you say that these are my constraints, like optimal power flow, for example, right? So optimal power flow says that, okay, I want to remove the violations, okay, and then I want to uh, use my generator pricing curve, right? Generator curve, so that whatever the optimization will give us, that will be the minimum cost and still violating the limit. Okay, so that's the optimization. Then once you run that optimization, you are so sure that with the parameter that you bounded your problem, you are going to get the best result if there is a result there, right? So that's the optimization one. That's guaranteed. That once you run optimal power flow, guaranteed that you will get the result optimal. Again, that's a centralized one, right? Centralized one. So how now, if we want to do the same thing, that's what I think you are asking. If you want to do the same thing with agent, can we do it? Probably yes, but probably it takes a lot of time to do that, right? So then you have to divide your optimal power flow problem on sub problems, right? And that sub problem should be handled by each individual agents, right? And then their results should be communicated between those sub problems, right? And then probably, yes, you will not have the guarantee like optimal power flow, but you will get much better results if you are perfectly decomposing your optimal power flow problem, Deepayan. So decentralized control is never gonna be optimal. Okay, I should not use never gonna be, never word, but generally speaking, decentralized control is not optimal control. Okay, decentralized control, we use the purpose is to be fast, right? We have seen several examples. We have seen examples on um, voltage control. We have seen examples on the protection control, right? Protection. So all are is fast. They are not optimizing anything. But if you want, there is nobody is bounding you to come up with, okay, if you I do this step 1, step 2, step 3, step 4, and then for this system I am going to get the optimal solution. So you can definitely work. Then I think time management will come into play if you really want that multi-agent should enforce the optimality on that one. Okay, so I think I covered most of that you were asking, but if I have missed Deepayan, please let me know.
Yes, sir. Yes, sir.
Okay,
Yes, sir. Yes. Actually, I received one review comments related to that only, because I'm basically from controls background. So they asked the question from the control perspectives. Because
right,
they say, okay, at the end of the day, you have to guarantee that your systems, overall systems, is stable. So how you're going to ensure that your control methodology is satisfying that condition. So they ask for the mathematical backgrounds. So
right.
that's why I raised this question. So
Yeah.
how
So you won't be getting, means with multi-agent decentralized control, you won't be getting. There is no
okay,
mathematics. It's only the hard work that you do to understand the system, knowledge of the system, right? Once you have enough
okay,
knowledge, enough input and output, and enough training, enough control that you have done, then you can be sure that under normal circumstances, your multi-agent system will give you local optima. That is the only thing that you can do. You will not be only go global, then we have to go with the traditional method for controls.
okay, sir. Thank you,
Okay,
sir. Thank you.
sure. Okay, and so there are several students, probably if you think that English is hard, okay, you can definitely talk to me with Hindi. मेरे को भी हिंदी आता है, okay? So तुम लोग हिंदी में मेरे से बात कर सकते हो. So don't be afraid that oh, I am going to make mistakes in English. My English probably you know that is not that good because I am from Gujarat and uh, I did my everything from uh, like under from kindergarten to 12th grade, everything in Gujarati. Okay. So, but again, you have to work hard if you really want to do something. You still have time. Okay. Once you complete your PhD and after 5-7 years, then you are done. Then you can't do something new. Okay. बट आप लोग मेरे से हिंदी में बिल्कुल बात कर सकते हैं और आई थिंक आई विल बी ग्लैड. मोस्टली मैं जब आंसर दूंगा तो मेरा आंसर इंग्लिश में ही हो जाने वाला है, बट यू कैन टॉक टू मी इन हिंदी. ओके, ओके, आई थिंक इट्स already time, and thank you, Deepayan. Very good question, very good discussions. I think that's what we are here for. Okay, so I think I will directly jump on to today's where is my say. Okay, let's go to here. Okay. So ready for the quiz? I try to be short this time because we have to. I think I covered it. Okay, I covered it everything that we talked about. Major part of it. Okay, I know there are a lot of technical, lot of programs. So actually, I can just create one for 4 hours on that one. Okay, but then you are not yet prepared. So that's not good idea. So I try to be very general. Okay, that one. Okay. Okay, here. So I think most of you are now familiar with the system. So you go to kahoot.it here. Okay, and type this. Now your name and your email ID, I think is not working, right? So type your name. Sorry, I'm doing something. Give me 1 second. Then we'll start here. Okay, then. I know some students may be having difficulty accessing it, okay? But let's start now. Okay, very good. Awesome. If you are joining late, Kahoot.it and game pin is here. Kahoot.it and game pin is here. Very well done. Okay. Yeah, I think it's working fast, right, today? There is no NG list. I just made it up. And that part everyone is knowing, so that's a good thing. IEEE FIPA. IEEE 519 is for the harmonics, and IEEE 1547 is for DG interconnections. Okay. All of them. Okay. I think all of them. So these behaviors are like methods, so that we don't need to program it. Means we can definitely program it, right, if you want. Swati and Trinath, both are leading, okay. asynchronously. Okay, agents pass. The agent execution itself is asynchronous. Okay, so asynchronous passing. Okay, Srinath. Okay, all of them. Okay, last one now. Trinath, Swati, and Nitish. Okay, why we have to take care? Because this method will not allow other behaviors to execute and receive the messages. So this method, we have to pay attention, okay, on that one. So let's see who we have on the podium today. 12 out of 14, okay. Nitish, good job. Srinath, 12 out of 14. Okay, 12 out of 14, okay. All of them, it's just a speed, okay. Swati, congratulations. And probably we have Madhu and Sunita for the runner. Hey, good work, guys. Let's see. 60%. So first day we had like 33%. Okay. Second day is 44%. And today is 60%. Okay. So we can just go to here, report. First day here. First day was the hardest one. But first day we had 65 students as well, right? So 33% result we had. And then second day, 47%, and we had 40 students participated on this one. And I know it's very hard, right? Means giving like 4 hours of your time, that too on evenings. So yeah, not everyone can do it. Means remember, 60%, this is good, 30 students participate. Okay, and I know exactly who did not do well, and this it will give me the report. Okay, so that's I use it for my courses here in WVU. So you see here I teach energy conversion course. I have like 16 plays on this one. Right? If you go and report, test. But anyway, it gives me the report, means to which student did good and which student did bad. Okay, so I can go back and probably give feedback to their students. Okay then. So thank you very much. Okay, so let's start our today's lecture. Okay. Okay, let's see. Okay. Okay. We'll start from here today. Okay. So this was the software that we use for with the Jade, but now that software is probably proprietary, and So we had a project from electric ship. So this software basically was developed for the electric ship, warship, okay, and to protect the power grid during war. Okay, how we can protect, how we can reroute. So with the available resources, because in war we don't know where your opponent is going to hit you, right, and what will be damaged. So a lot of simulations and like 10 years 15 years project on this one. Uh, but in that one we were using we simulated this one with a resistive companion form model. It can be applied to any, basically uh, any simulation that as a student you want to do. I is equal to gv minus b. Okay, so you can build your model in this format. You can embed it, whatever color, however you want to image, you can edit and simulate. And this is not just electrical, it was, you can incorporate mechanical components, general, and then do the co-simulation in the same. You can also do a remote simulation. So you have a half part of the network in other part of the world and a half part is another part of the world, and you can still co-simulate that. So those kind of facilities were available, but now it's not there. But we definitely have Jade, right? So we already talked about Jade is written in Java for the development and runtime execution of peer-to-peer application. Okay, very important one is peer-to-peer is the keyword here. Jade is multi-threading, helps in case any agent needs to execute several tasks in parallel. Agents execute through behaviors, communicate through PIPA specified language, agent communication language, ACL in short. Okay, the local name of agent is converted into globally unique ID. So if your agents are part of the same system, okay, then anyone can access it, anyone can reach it again. If that agent really wants to receive the message and send a message to that agent. So general, this is very important. So now I think Dipayan or someone who was asking that how we can do it, right, with MATLAB or any other software means. So general structure, so you have all your agents are running in Jade platform, right? So Jade has main container, and then I think we talked about main container and sub container. So you can have multiple sub containers, right? And then you can add your agents. You can have your multi-agent system here in the Jade platform, okay? And then you can run your MATLAB here in Simulink, okay? So so from MATLAB, as a student, right? So we are working on some kind of concept, right? We want to make sure that our concept or some kind of algorithm, distributed algorithm works. So what I would suggest is you develop your Simulink model, simplistic, very simplistic. Take couple of loads, couple of lines, and couple of not even generator, just voltage sources or current sources, okay? And just read measurements, okay, from the MATLAB and dump that measurements into the text file, okay? And I think it is doable because in MATLAB you have functions, okay? In functions you can write your own code. So in functions, so in MATLAB Simulinks, you use functions, okay? And then you, in that function, you can just write your code. Open the file, dump the data, close the file. Open the file, dump the data, close the file, okay? So that way you can send the data to the text file, okay? And the agent will be reading those text files. Now, the problems comes when, because your simulations is running in probably microsecond and nanoseconds, okay? So we have to put attention to it that when you are writing or reading from the data file from the MATLAB, I mean the MATLAB generated data file, that there are very high chances that whenever you are trying to read the data from that file is not readable because the MATLAB is accessing all the time. So you have to take care of in your programming that if file is inaccessible, you try, and then you will get the data, okay? But in this case, what we were doing, we were in Microsoft had IIS server services. Okay, so we were dumping the data from here, get signal and get signal and set signal. Those were the commands available. Someone developed computer science PhD student, I think, developed that one. So you can just use that one and send the data to server. Okay, IIS server. And then in VTB, we had a same get signal, set signal, again developed by some computer science PhD students, and then you can receive it. So again, this when you are getting the data, these are all asynchronous data. It's not like a PMU, right? Synchronized, same time instant data. So very, very important when you are developing, because generally that is the case in the multi-agent system. You're probably not getting the synchronized data. But again, you can definitely assume synchronized data, because now with advances in phasor measurement units, and even several, I think, smaller devices are coming up from the APRI, that even distribution system, you can have micro PMUs, right? If you are doing PhD, probably you might have heard about it, micro PMU. So you can assume in your simulation that this data that you are getting is synchronized. Or you can definitely, when you are running your power system in MATLAB, when you are dumping the data into the text file, okay, you can just add a time step, right, in the simulation time step. And then whenever you are reading, you are taking the data, but synchronized data that you will be pulling up from all the text files, all the measurements basically, and do that simulation. Okay, so many softwares had to work together for this particular case. We had Visual Studio, Java to J, SDK, right? Jade, VTB. So in your case also, right? Jade and MATLAB, okay? And then whatever the system that you have, Windows system or Mac system, I think both should work this one. So that's a good thing, because Java is a platform independent, right? We already talked about it, this one. But at least each agent has a setup method, action method, done method, and take down method, okay? Each agent instant is identified by an AID, agent ID, and AID is unique name of agent. So what does it mean? So you can write, this is, I think, kind of architecture for one of the switch agent, okay, one of the switch agent, very high level architecture. But switch agent job is to just get the data of the current or voltage or whatever you want to, in this case is current, right? So just to get the current data from the system at the end, right? So you get the data from the system, and so you have multiple switches, right? But you write one agent program, and then you provide that agent that you are getting the data from switch A, switch B, switch C. And that switch A agent has a neighbor agent, right? Probably a load agent, okay, or another switch agent. So then for that switch agent A, okay, the information that is going to change is the fault current, okay, and its neighbor and where it is measuring, right? So then you can use the same agent for multiple switches, okay? So that's exactly what it is saying. So each agent instant is identified by an AID, and AID is unique of that agent, okay? So you can have 10 switch agent exactly doing the same thing, but for 10 different switches, okay? An agent can execute several behaviors in parallel, okay? Templates are defined so that messages are received by intended receivers, okay? ACL messages passed between agents are characterized by intended receiver, that conversation ID, type of message, and content of the message, right? Here, so we have a behavior, fault count behavior right here. And then in that behavior, then we have a fault query behavior, right? So it's calling, measuring, basically think of this as A phase, B phase, and C phase current is getting from wherever it is getting, right? and then it is comparing each phase and then if it is more than the desired, generally 1.5, but I put it 5 here, so more than the maximum load current, then you say that there is a fault, and then you send the messages. Okay, and then this one is receive reply behavior. Okay, get messages. Okay, so when it's reading, because other agents may be sending messages to your agent, right? Fault action behavior. Okay, so in that one, whether you want to close or you want to open or you want to send the message to another agent. Okay, action, sorry, in action you are doing that, open or close. Okay, but in action, fault receive action behavior and fault action behavior. So in action, probably you are receiving and then sending a message to another agent. In that receive action means that it is saying, another agent saying is open, then it is you are sending a message to open the breaker. So it is very doable in MATLAB Simulink. Okay. Okay. So probably for this one, I need to use full screen. Give me 1 second. Okay. Okay. Because I have some. Okay. So what I think we have a paper on this one. I think a transaction paper on multi-agent system. One of the key paper in multi-agent system. Okay, not the paper, but one of the key paper of multi-agent system. Okay, so very simple, right? We already talked about it, but now these are the details, more details on that one. So another problem that we talked about, very practical one, we had like more general side. So here we have a little bit more detail. So once you have the fault here and you breakers remove the fault, now these 3 loads, right, are de-energized. Okay, and you have another one just switch here, normally open switch, and another feeder. You can think of as a 2 feeder. So now forward propagates message, query ref and restore. So all are going to send the message. Okay. So you have a load, we'll have load restore start behavior. Okay. Switch, these are switch agents, switch restore behavior. Okay. And then that message will be received by this agent. Okay. Then if the normally open agent will change the message from query restore to query ATC, available transfer capacity. So now this agent is searching, asking for the available transfer capacity, and then it is forwarding. It's completely decentralized, okay, completely decentralized, and still it is faster than normal, where you have to really go and look at it, distribution system. There is no such methods available in distribution system, okay. So switch ATC forward behavior, okay, that is, so we are still querying, but now we are changing that instead of restore, this agent is changing the conversation ID, ATC, okay. So then it will go to the feeder agent, basically here we are saying generator, and generator will inform, right? So it's querying, generator is informing, and that message is passing to this one, completely decentralized, not sending directly to another agent, okay. Inform ATC step 3, this one. So generator ATC inform behavior, that is everything is coded in JET, okay. Switch ATC behavior, inform behavior, now this one, right? So propose, then it will change, this agent will change, propose, we are proposing this much available ATC, okay. Switch avail ATC behavior, so that is coming from this agent, okay. Load ATC action behavior, that message is passed through one agent to another from the switch to load, okay, and then load agent will be receiving that message, whether it has to shut down or whether it has to keep it on, means to close the switch, okay. Very general. So these are the behaviors. Do I have more? Okay, we have one more, okay. So that is another system. So that is where we have a DG, okay. So at that time it was very new, right? Microgrid is very new at the time. So Microgrid, very simple, one DG applications, and very valid in current scenario as well, okay. So in this one we have moving agents, okay. So that agent moves, okay. Let's see if we have seen that one, okay. So we added a moving agent, so capability from that one, okay. So it's moving from one agent to, I mean, one place to another place, right? So generator, breaker, switches, loads, okay, and then going and requesting. So move load request behavior. Load reply behavior. So if the moving agent when goes to the load agent, it asks for what is your priority, what you are consuming, okay, and those kind of information. Generator is asking from the generator, right? We have one generator, one DG here. So move. So these are the behavior involved with the moving agent. Okay, one agent here. Okay, and then here inform before island. Okay, before island, what this breaker was seeing. Okay, very simple. Breaker island restore behavior added there. So these are the messages here, right? Query ref, loading, inform before island, right? Propose, set load, right? So these are the messages so that you are sending, you know that not any other agent should be reading it. So intended receiver. So that is why we use this kind of messages. This one. Similarly to the address, basically, okay? Move island detects behavior and load action behavior, okay? So very general case, very typical, very valid for any distribution system and any distribution system with uh, even with a couple of generators, right? This microgrid basically, okay? And here is forward, backward propagation, right? So here once if this island is not sufficient to satisfy the load, then it will go and ask the power from another feeder, okay? Okay. So the actual work that an agent does is carried out in behavior responsible for restoration and load setting if necessary. So these are all the Java file that we wrote it, okay, that we wrote it for doing the restoration on this one. So now details of switch agent, okay. So we talked about the switch restore behavior, switch ATC forward behavior, switch ATC inform behavior, switch avail ATC behavior, switch avail ATC action behavior, right? So what are the messages? Query ref message, restore message, content, switch or load, right? Local name, status, those are the things received by this behavior, okay? This behavior receives query ref ATC. So there is no clear distinguish. We are clearly distinguishing between these messages, right? So we don't want that this behavior should steal the message that we are expecting in this one, right? That we were talking in our yesterday's lecture. Similarly, switch ATC inform behavior. We have inform and ATC, right? Content remaining ATC. Switch avail ATC, propose avail ATC, supplied ATC. So we have some kind of enforcing method that intended behavior should receive the intended messages, basically, right? Propose, ATC reply behavior, accept or decline, okay, based on that. So these are the messages received by this behavior. What are the messages sent by this behavior? So we have query ref, restore, query ref, ATC behavior, query ref, ATC here, upstream, receiver, right? Then inform, ATC behavior, remaining ATC, downstream, receivers. Similarly, other methods, okay? Other messages. What once you have this, what did they do, right? So description, the switch restore is receives message from either load agent or switch agent and saves the message content in predefined format. So this saves the message, okay, on this one. Now switch ATC forward. So saves sender's unique agent ID and forwards the message. So switch agent, this behavior knows who requested information. So it stores that information and forward it to another agent, right? And we already saw that one, right? That's going to be difficult to go back on this one. So that is why I was using that. Okay. This switch ATC inform behavior receives the message from either generator agent or switch agent and forwards to the agent who asked for ATC. Okay. This behavior description does load setting. load allocation, and best statistic selection. So this is the algorithm basically, right? So all the communication now, this is the behavior that really decide local decision it is making, local load agent that are nearby, neighbors of this one, whether we should, it's deciding whether we should set them, allocate them, or if it is a normally open switch agent, etc selection when you have multiple paths available, okay? Sends close or open signal when content of the received message is accept or decline, right? So it's whether you want to accept and close the switch and get the restored, right? Load get restored on that one. Details of load agent. Load agent, we have load restoration start behavior, load avail ATC action behavior, move reply behavior, and load action behavior, okay? This behavior doesn't receive anything, okay? Because this behavior is just getting the measurements and seeing if there is a loss of voltage, and I should initiate the restoration, okay? So that is, so it is, this is the message sent by this behavior, query rep, restore. See what are the contents, right? So performative, conversation ID, and content. So in the content saying that I am the load, this is my name, load agent, this is my status, what was my loading, and who are my receivers, downstream receivers, right? So again, you have to formulate this one up according to your need. Detects the loss of voltage and send message with pre-fault loading and critical or non-critical load status to this neighboring agents. Okay, so what is his job in this behavior? Detect the loss of voltage, right? And again, when you are detecting, because when you are doing simulation, you see 0 one time, right? So it depends on you are really accessing time domain signal, or you are converting that time domain to RMS. So you have to take care of those very basic one, right? Means understandable. Most masters and PhD students should understand that. Similarly here, load avail ATC action behavior, propose, right? Performative ID, conversation ID, avail ATC, content close or open, and remaining ATC, right? On sends message, again propose, ATC reply. Remember the conversation ID changes here, content accept or decline, and receivers are downstream switch agents. Sends close or open signal when content of the received message is accept or decline. Does best ATC selection when needed. Okay, so it also does the best ATC selections. Okay, when this load agent is representing. That's nice. Okay. So does best ATC selection when needed. Okay. Let me finish and then comment on that one. Move reply behavior, performative query ref, loading. Okay. Here the send message is inform and other things, right? It means you got the point. Receives the query from moving agent, okay, and sends its current loading condition to the moving agent. So it's still in the same load agent behavior. So load action behavior sends open signal to itself when content of the received message is open. Okay, just one comment on kids, because some of you are like new parents. Advice from the older parents. So when generally our like typical sense that we have in India is that अरे ये बच्चा है इसको क्या समझेगा, right? And then we ignore their questions. So I highly recommend, even if ये बच्चा है पर अगर कुछ पूछता है, reply the right answer. And if you can't reply the right answer, don't give the wrong answer. Okay. And that is the thing that I notice here. Here the kids are more mature than our Indian kids, because that is the, I feel that that is the thing that we are doing to our kids. We say, when they ask questions, we say, oh, bacha hai, I should ignore. No, give them the right answer, even if it's a difficult one, even if you then think that he or she should not know that, but he or she is asking question, please give them the right answer. Okay, just my 2 cents on that one. Okay. Details of breaker and moving agent. So what are breaker agent? Breaker agent has island restore start behavior, and similarly send message, sends current magnitude and real power through the breaker, that is it is measuring to moving agent. Okay. Then move agent has these are the behavior: move request behavior, move receive loading behavior, island detect behavior, some of the message template for the sending and receiving. Move agent requests current loading from loads and current generation from generators when it reaches the respective locations while it moves. Okay. Receives current loading. This one move receive loading. Move receives current loading from loads and current generation from generators when it reaches the respective location. Island detect receives a current magnitude and real power from breaker agents, right? That's what it is sending here. Decides the load that has to be shared and sends open. So again, algorithm is here. So island detect decide of move agent that which load has to be sent, because it has all the information. It's going through everywhere. It is storing all the communications, and based on that. So extremely complex if you think about it on this one. And it's dynamic, right? It's happening very dynamically on this one. You also have a generator agent, right? Generator has agent has two behaviors: generator reply behavior, generator ATC inform behavior. Okay, and then you have a send or receive messages here. Okay. Mm. Generator reply behavior receives the query from moving agent and sends its current generation and maximum capacity to the moving agent. Okay. Generator ATC inform behavior calculates its remaining ATC from the current loading given maximum capacity. Okay. So again, the heart is in here for the generator is the ATC inform behavior. Okay, don't get scared. Okay, this is generated automatically. So there may be a command, something on that one. So this is folder, restoration folder. Okay, and these are the switch agent.java file, generator agent.java file, load agent.java file, breaker agent.java file, move agent.java file. So in that file, we have for switch agent has switch avail ATC action behavior. So this is a behavior method. Okay. Load agent has load avail ATC action behavior. Okay. And then switch ATC forward behavior. So this is switch restore behavior. We already talked about it, right? So you can see that there is a behavior and everyone has action and done method. Okay. So this restoration package does the restoration of the two systems that we just saw. I just showed you. Okay. And then it uses, what are the capability it uses from the JADE, right? Parameter exceptions, message template, ACL messages, simple behavior, delay behavior, right? Behavior, then agent. Those are the capability of JADE is used for this restoration package. Okay. So you have switch ATC inform behavior, then load restore behavior. So these are behavior, these are methods, but only the Java files are these files. Okay, mostly in pink color. These are the Java file. This agent is from the JADE. Okay, so this is a complete package for doing restoration of radial system and restoration of radial system with distributed generators. Okay, very complex, almost 2.5 years of work on this one after understanding. Okay, remember, is detail. You have to be keen to do that. Okay, because otherwise you will get frustrated. And anywhere means anywhere, and if you are doing something meaningful, it is not simple. Okay, something meaningful, it works for general what you are saying. Generalize one, minor tweaks you have to do. So master and PhD, okay, all the students, it's not simple. You cannot just simply achieve just spending 1 hour time or 2 hour time or 6 hour time a day on your problem. You have to constantly working, constantly searching, attending conferences, reaching out to experts. Okay, those are the things needed. Okay, you will get stuck. Probably your advisor will not know the answer. Okay, then you are the one. Remember, you are the one that's what we did. Okay, when we got stuck, because you are doing PhDs, master level work, nobody knows the answer. Means because we don't have that kind of infrastructure. Yeah. But at least nowadays you can communicate worldwide, right? ResearchGate, if you have not heard of it. One is Power Globe, very good. In PowerG, good platform. ResearchGate, good platform where you can really go and ask your questions. So these are the platform, and I have not seen any question unanswered on this platform. Okay, so if you ask, you will get some kind of feedback to your answer. Okay, and another thing is that how much you are willing to share, because you worked so hard to find the right question, right? I mean, that answer is not available in any literature anywhere. So you are at that stage that you got the right question. Now, if and you know that if I do this, probably I'm going to get the answer for this one. So coming up with the right question that no one has solved, okay, it takes time. Okay, so very important. This is crucial to understand as a master's and PhD student. So that you are the responsible, not your advisor. Okay, you can't blame your advisor. Okay, because we don't know. Means we know the very high level umbrella. We know whether you are doing right or wrong. Okay, but what needs to be done, that is as a student. Okay, a student has to but generally, if you are persistent, if you are communicating every week, detailed communication, if you are doing, I think most likely 90% time that you will get the feedback, right feedback from your advisor. Okay, but that 1% or 2% cases where you are stuck, means no one knows your answer. You are reading papers. I remember when we were doing for DG modeling, we'll talk about it, that we read every single paper available on the market, every single paper that we have access. Okay, 50, 60 paper, every single line of that paper. We couldn't find the answers. Okay, we couldn't find the answer that we are looking for. I will talk about it. Okay, what that answer and what was that question. Okay, so very important. Okay, so here now we have 39 agents on this one. So we have 2 generator agents, 25 switch agents, and 12 load agents. Okay, and build it in Jade. This one is think of as a running the power system in MATLAB. We were running in the BTB here. Okay, and we discuss all those communications, right? These are normally closed switch, normally open switch. Okay, and when there is a fault, okay, this breakers opens up. Now load 2 to load 6 are de-energized, and they have a different priorities. Okay, so load 6 is the one. See what it message is sent by load 6. Load 6 to switch 21. Okay, so probably this may be a switch 21. Okay, so it is saying I am a load agent is sending load agent 6. My priority is very non-priority or priority. And then what was the loading before I saw there was no voltage, means I lost the power basically. Okay, and then all these communications happen. Then another load 4, these are asynchronous messages. Okay, then load 4 is sending, load 2 is sending, load 5 is sending, so load 2, 3, 4, 5, 6, right? 2, 3, 4, 5, 6, and that message. Okay, normally open. So these are all the switches. When receiving, it is just storing that load. So here this switch is storing only this information. This switch is storing both this loading and this loading both, right? Similarly, this switch is storing this load and this load both. This switch is storing this load both information, and all the requests coming from other agents, right? This switch is storing this loading information, this loading information, right? So locally, everything is locally done, local communication happening. Okay, and now if you see here, somewhere I see accept message, but I don't see. Okay, So here also we are, did you see the fault? No and open, right? So here, these two agents are detecting simple, okay, overcurrent fault only, okay. You can definitely do differential relay scheme here very well. You can see here, accept, close, right? All these messages are being passed between agents. So all the communication is happening. When the message comes to here, the conversation IDs will be changed, okay? And it will be ATC, and that message is now gone through all these agents to the source generator agent, okay? And generator agent is saying here that this is my capacity. I can supply this much, 338, okay? And based on that, it is passing now here, that message is passed, okay. And when it comes to this agent, let's say, for example, okay, so this agent knows that I have a downstream is this load, okay, and it also knows that there are upstream load, okay. But if this, based on the information of 338, if it can supply to all the loads, then it will just send a message to this load agent to close the switch that is not shown, okay. And then this load is restored. And let's say if I think probably we may have a case, okay, this one. So in this one, I think full restoration, right? Full restoration. So it has enough capacity. All the agents are sending messages and then restoring individual load because it has enough capacity, this source to restore the loads, okay. And then switch is closed, all the loads are restored, okay. And this something like this you will see in your simulations, okay. So here there was a fault, right? Fault current, very few cycles and gone, okay. Generator 2 current. So now you can see how fast it restored the load, right? So generator 2 within like 100 or 150 milliseconds, all the loads are restored. Here you can see load 2 was disconnected, got the power back, right? Maybe 100, less than even 100 milliseconds, okay? All the loads. And you can see here the close signal was sent to the normally open switch agent, okay? So this is can be done very well, I think, with MATLAB. Okay, now partial restoration, where you don't have enough power, right? And then you have a priority load and non-priority load, right? Important load, very important load, and non-important load. Same fault, different priorities, right? So here now asynchronous. Earlier you saw that load 6 was able to send the first message, right? Here, remember, asynchronously and simultaneously done from all the agents, right? So LA3 is sending the message to its neighboring upstream agent, right? So and then this is the information passed to this one. And so LA3, so all the agents are sending their information. That information is passed through this normally open switch agent, okay? And then normally open switch agent will change the conversation ID, request the available power to the generator agent. Generator agent says that this is my availability, 153.23, right? 153.23 availability. And now they see all the calculations are happening. 153, one of the load here, right? Switch is deciding this one. This one is deciding where is the load. Close, right? So it's sending a load 3 message, you can close, right? So because it has available here. Then here, load 2, accept it, right? And then again, this one, this switch agent is sending a message to load 3, right? Close this one. See how the available capacity is decreasing. Again, it is happening in asynchronously, okay? And in the system. Intelligently, our agent, like switch agent, what is 19, decides to set load 5. Okay, so this may be a low priority load, load 5, 35. And if you do all this, I have not run the optimization, but this is locally, right? Because local information, locally deciding, not centrally. So you may get that not optimum results you may get, okay, but you definitely get the faster result. So you may trip the load that may not, if you run the optimization, probably you will choose another load, Dipayan, in this case, right? So that is kind of a disadvantage, right? But the faster, quicker, and decentralized, right? There is no bottleneck here, right? Everybody is communicating. So local is deciding that it should set this one load. But if you, again, if you study hard, work hard on your algorithms and your system, if you understand, I think most likely you will get very good results. Okay, very good results. So okay, and then close, right? So all the loads except load 5 are restored. So load 5, so fault is gone. Now load 5 is restored quickly, right? So in this case also we have 39 agents. So all 39 agents are working together. Remember, switch agent, only one file, different behavior, right?
Right?
Okay, can you hear me?
Okay, can you hear me?
I don't know, it's echoing here. Okay, I think that's gone. Okay, so that's a partial restoration. And then, so now we have two signals here, right? So one is closing the switch, okay, and then opening the switch here for this load. So we are sending load 5 status, right? We are opening this one, switch 34, we are closing that switch, and all the loads, fault current is removed, generator 2 ramp up, right? And then all the loads are restored, okay, on this one. Okay, partial restoration on this one. So in this one, we have 34 agents. Okay, so now we have multiple feeders, multiple paths of selections, right? And this is these are all normally open switch between feeders, okay. And then it's very simplified, two loads, each feeder has two loads, number of switches. There are 4 generator agents, 22 switch agents, 8 load agents, total 34 agents in the system. Normally closed, normally open. Okay. Once you have a fault, it is sending messages between switch 9 and switch 10 and opening the breakers. Okay. And then load 6, one load is not getting the power. Okay. And let's assume that this is kind of a military system or important system. I think we did it for the ship system. So this was something like that we had at that one. Okay. Electric ship system, warship, and perfectly you can call it a microgrid as well on this one. Okay, microgrid on this one. Okay, so what is going to happen? This load will start the restoration process, right? So load 6 lost the power, lost the voltage. It recorded its previous loading conditions, right? So I am a load agent 6, very important. And this was my loading, right? And then it will send the messages here. So now with this switch, you have 1, right? 2, and then these are the 3 options this switch has, right? So it's going to, so everyone is going to send a different loading, right? So different kind of 143 here, another is sending 63, right? So different values are sent. So this message, this switch agent 15 is going to send a message to switch agent 24, switch agent 25, and switch agent 26. Switch agent 26 goes to the source that message asynchronously, locally, from one message, one agent to another agent will reach to this generator agent. This generator agent will provide the available ATC. Okay, similarly for switch 25, this generator 4 will provide available ATC. Switch 24, source 2 will provide available ATC. Now switch 15 will receive all these 3 ATC, right? So we have one is 143, another one is probably, I don't see it, 43, right? 63, and then 43. So different agents provided different loading conditions, right? So here we are saying that, okay, we are declining. So switch agent 15 send a decline message to switch 26 so that it's gone. And then again, switch agent 15 send a decline message to switch 24. 24 is this one. So definitely it's choosing this switch 25. Let's say switch 25. Where is switch 25? So that was the largest one, right? Switch 25 was the largest one. So switch 25,143, switch 2663 available capacity, and switch 2443 available. So it automatically chose the largest available capacity to restore the load. Okay, though it may not be needed, right? I mean, technically it's 24 here, but it chose the largest possible. Okay. So these are the responses. No change in other statuses. Only switch 25 close, right? Switch 25 only close. No change in this one. That's what we are seeing. Generator 1 current, load 6. Generator 4 current, no change in generator 1. Generator 2, only generator 4, right? Because generator 4 now is supplying additional load L6 here, right? So generator 4. So this one. Okay. Okay, modified shift system. Okay, modified system. These are the bus data, branch data of the system. Okay, now there is a moving agent, if you can see it, right? So we have a case with DG now. We are doing the restoration with DG. Okay, restoration with DG. On this one, so in this one we have 12 agents. Okay, 4 generator agents, 6 load agent, 2 breaker agents. Okay. Very simple. We are just doing this one with just for the DG on this one, right? So we have a DG1 here. There is a DG2, DG3. So perfect. You can call it a microgrid system, right? Microgrid system. But again, we will talk a lot about microgrid tomorrow. Okay. Tomorrow we are going to talk about it. So here, when moving agent is moving everywhere, collecting all the information, and it's moving with the information everywhere. Okay, once you have a fault here, you remove the fault. Okay, and then you will have an island. Okay, that island may be self-sustainable, that island may not be self-sustainable, right? How you can decide whether it is self-sustainable or not if load is not equal to generation, right? Means if load is much larger than the generators, okay, or load is, even in cases where your load is much smaller than the generators, okay, much smaller, that does not match up the ramp time of this diesel generator, how fast they can change it, right? So in that case also you may have a unsustainable island. Okay, so it should be, again, a detailed study is needed. Very important is the detailed study is needed. Okay. Okay, so in this case, I think where is our breaker agent? Let's see what is happening. Load 6, then load 5 here, load 4 moving agent. So like 3 additional and the circle. Okay, sending them, loading to moving agent. Okay, so all this information, DGs are also sending to moving agent. Okay, and then generator agent is sending, right? This one is so this moving agent is sending loading to generator 1. Okay, generator 1 is sending that loading available probably to the moving agent. Okay, here different load agents are sending load A1, SA04. Okay, and then priority, non-priority, and what was I was consuming before. Okay, BA11. Okay, BA11 6.7 and 10.97. Okay, and then open the message. Okay, let's see here, S16. Okay, S16 is opening up the message here. Load 5 is dropped. Load 5 is dropped, right? So moving agent is sending a message. Okay, not the neighboring agent in this case, right? So moving agent is deciding which load to send based on the information that the moving agent received. Okay, and then the island is self-sustainable, and then everything is restored. Okay, so that is one case of load shedding. Okay, now these are the things that we are going to see in the simulations. DG3 voltage, right? You will have a voltage drop, right? Little bit when you have a fault, right? This is a fault. you have voltage drop, DG2 current reduce, DG3 current reduce, DG1 current is not, okay, and generator 1 current is reduced after the fault, okay. Load, all the loads except load 5 is restored, right? All the loads except load 5 is restored, okay. So let's see DG1, DG2 and DG3, right? DG2 and DG3 now is not connected upstream, right? This one, so their power is, and DG1, there is no change, almost no change in the DG1, right? Power from the DG1. Here, no change in DG1, but you see DG2 and DG3 is reduced, right? This one, current is reduced, okay? And it's not, even if it is reduced, but it doesn't have the enough power to supply that load, okay? Now we increase a little bit bigger system on this one, okay? We added a path here, additional path, okay, to utilize what we developed before, radial restoration scheme, right? So again, a lot of messages between moving agents. So now we are also adding our earlier development here, okay? Okay, so once you have a fault here, okay, and then fault is removed, now you have an island. That island may not be sustainable, may be sustainable, depends on, right, what is happening, okay. But generally the frequency, okay, so here we are not doing the frequency one, okay, so here we are considering the voltage one, okay, and then the current aspects of it, okay. In this case, load 3, that we already saw that, right? So when we said, we saw that in earlier case that load 3 was set, okay. Now load 3 will send a message, okay, that this was my loading to all the switch agents. So it automatically decides and then pass that message to switch agent 30. Switch agent 30 is now going for availability C to this DG2 agent, okay. DG2 agent will say that generator 2, my available capacity is 30, the load was 14, right? So it makes sense to close the switch. So, but it decide here, okay, and then close the switch here for the load, okay. So that is who is sending, switch 9 is sending the close message to this one, and then accepting the load, say load 9 is saying accept the message, right? And then we have close this one message, and then load 3 is restored, okay. So all this is decentralized control, okay. Classic example of decentralized control, okay. These are the responses that you see in your simulations, okay. You can see that load 3 is restored, and then it's quickly, right? The important here that we are doing the quick restoration, okay. Quick restoration here. Okay, so I think it's a good time to take 5-10 minutes break, okay. So let's take a 10 minutes break, okay, and then come back. So whatever the time there, add 10 minutes to it, okay, and let's come back and then discuss more about it. And then I think we are almost done with this one. Then we will start a numerical simulations, okay, numerical methods and resistive companion form method that I promised to Dr. Prerna, okay, and MNIT and all of you, okay. So let's come back in 10 minutes, okay, 10 minutes from now. Thank you, guys. Okay, we'll start in 1 minute.
Sir, I have a query. Like,
Yeah, go ahead. Go ahead. What's
yes,
your name?
sir. Swati.
Swati.
Sir,
How are you, Swati?
I am good, sir.
Okay.
Sir, have you done some sort of co-simulation? Like, you have designed something on software you were telling, like MATLAB Simulink, and then you have taken those switches as agents, and then you have uh, done the coding on Java JDK platform, and because of that, they are communicating. So, is it something like this?
Okay. So, okay. Let me see. Do I have anything file? Okay. So, any power system simulation where you can kind of send the data from that simulations to external file. Okay. And once you have that file, means for us is measurements, right? We want the measurement so that we can do a restoration. If we don't have the measurement, then we can't do the restoration. So any simulation that can give you the measurements, okay, and then you can you can apply these agents on that one. I have seen a lot of hardwares like RTDS. I think you were the one mentioning RTDS. Is that Swati or someone else? I don't know.
Yes, sir. Yeah.
Okay, you were. So in RTDS also I have seen a lot of development happened with multi-agent system. So they use this JADE, embedded that JADE into maybe Arduino or some other platform, and they were getting the data from the RTDS. Okay, so in RTDS, you have a facility of analog and digital that you can tap into the simulations. So in real time, right? Means we say real time, but it's because it's 10 to the power minus 9. So that is why we call it real time, right? So we get the data, you embed this one, and then you can send the data back as well. So you can do this very well in your with RTDS, okay? But again, it's not fast enough, but at least will give you the decentralized flavor. And then if you really need the faster, then you have to embed your algorithms in some kind of microcontrollers that you can really use it in real system. Means test it. So there are papers out there that they have used multi-agent systems on the hardware and did the co-simulations with RTDS. I mean, tested on RTDS. Does it make sense, Swati, for you?
Yes, sir.
Okay.
It is a type of a co-simulation, and they have coded on, means they, with the help of some hardware, like you said, Arduino, and then they are able to communicate the hardware
That is
devices. I
that is.
Okay.
So if you have to look and if you are interested in that kind of work, Florida State University, they have done that kind of work, and
Okay.
the professor name is David Cartes, Cartes. By now he probably retired, but his paper should be there. David Cartes or Dave Cartes, DAVE or David DAVID Cartes, CARTES, if I'm right. Yeah, but Florida State University, they have done a lot of work on that aspect.
Okay, so I would find papers on IEEE Explore if I want to
Yes,
just
yes.
go ahead
IEEE
with
or
this.
yeah, IEEE Explore. I don't know whether they have it in IEEE, but it was like all SIP systems. So see if you can find it. Okay.
Okay.
If you don't find it later, send me an email. I may have somewhere, so I just need to spend maybe 15-20 minute look for those papers. But you should be able to most likely. Yeah.
Yeah. Okay, sir. Thank you so much, sir.
Okay. Okay. Any other questions? Sorry, I forgot to ask. Any question that you may have? Okay. Sorry, I am again wearing the jacket. Our controller has gone bad, and his outside is probably 70, but inside is 60. Okay, so 60 temperature, 12 degree Fahrenheit. I am sitting here. Okay. Any questions? Okay, I see some chat messages here. Yes, yes. Okay, I think I answered that one. Okay, let's quickly go to 2 or 3 slides and then we'll jump back to, with time constraint, I will jump to the next presentation. Am I sharing my screen? Yes, I am. So we did also one, we implemented MAS with inter-PSS. So inter-PSS is just a power flow written in Java, okay? So we use bus agent, SVC agent using this one. And we implemented on 118 system, 118 bus system. So again, detailed study, maybe almost 6 months, 8 months, just figuring out where may be the problem. Okay, lots of simulations. I generally say, instead of word lots of, we say Monte Carlo. Okay, Monte Carlo simulations we have done on this one. So you can see a maximum impact region and buses under influence. Okay, so if you have some kind of control, this will be your maximum impact region. Okay, buses influenced. Okay, these are the buses influenced on this one, on controlling the voltage. Okay, so these are different influences, reasons that we identified. Again, I think there should be a paper in IEEE Explore on the details of this one. But this is voltage, then net power voltage we are comparing, and voltage of inter-PSS. So again, as a master's and PhD student, so anytime that you are working, right, so you need some kind of benchmark system. If you don't have benchmark, then no one will believe your results, right? So here we are saying, okay, we are using inter-PSS, okay, but we are comparing with benchmark. Okay, so inter-PSS power flow and benchmark power flow we are comparing with 118 bus system on this one. Okay, and we are saying that's almost matching, right? Almost matching, 1 or 2 places except, but most of them are matching both the world. So we are certain, means when I see this result, I can say that, okay, student is doing good job, right? So means, okay, he has the knowledge, he implemented here, this is a base knowledge. Okay, and then based on the sensitivity, based on Monte Carlo simulations, he's coming up with this is what I analyze. Okay, a lot of hard work. Okay, just coming up with this diagram on this. And then we are applying the agents on inter-PSS, basically utilizing the measurements on this one. So dynamic simulations of this power flow. We are just running time series power flow on this one. So bus voltage is before agent and bus voltage is after agent actions. If we did not have the agents, then we would not be able to resolve this violation in the time that we are resolving here. So multi-agent is very helpful. Means when I presented on secondary control, that's exactly what we are doing on 118 bus system. Okay. Okay. So I think, and then we'll talk later on this one, other aspects of it. So let me go back and use next slides. And I really want that to show you some new capabilities of MATLAB. Okay. Later today. So just hold on. So if I can finish this one, maybe an hour or 1.5, then we have quite a half an hour or so to go over the mechanism. It may not be fully sufficient, but I think just to give you the flavors, right? Means what can be possible, what you can do. Okay, so numerical techniques and resistive companion modeling. Okay, that's the topic of now. We have different, if you are doing master's and PhD, and if you have not taken numerical methods, lecture it is a must for, and if you are involved in some kind of simulation, so it's good to know all these techniques. Okay, not, we don't want to be expert, but at least we should have some basic knowledge. So we have numerical method, one step. Okay, you can just get the results by just using the prior. So it's a one-step method. Okay, so just prior knowledge, prior step, and you get the next step. Multi-step, prior and the current to get the results. Okay, explicit, very similar to multi-step. Okay, so to calculate the next step, solution, you need your prior solution and current solution as well. Implicit just require the prior solution. Okay, that's uh, implicit method. Okay, is computed based on the values of x and f at current time step. And okay, so I reverse it. Explicit is the one that is explicitly based on x and f previous step. Okay, that's explicit. Implicit means you have the values of your current time step as well as previous time step. Okay, and then you have to do iteration when you have this kind of thing, because you don't know the current time step. Okay. Property of numerical integration methods. Okay, one, numerical accuracy, right? Very important to understand. Truncation error, round of error. Truncation error is due to termination of an iteration process before final convergence in solving the implicit difference equation. That is generally the case, right? It means when we are doing the power flow, we set the convergence criteria that milli volt, right? Or microvolt. So that's our termination criteria. And then we have to live with the error, right? And that is what we can do best. 10 to the power 9, 10 to the power minus 6, 10 to the power minus 3. That's our termination voltage criteria in the power flow. Round of error. Round of error is due to the inability of the computer to represent numbers correctly. If we use more bits, this type of error will become negligible. So 64-bit, right? 32-bit we had earlier computers, now we have 64-bit you can get, but still again it's 64-bit. That is the maximum you can do, right? So that's our round of error we are definitely going to see in our results. And numerical stability. Okay, I think we will be doing an example probably. Numerical stability. The stability of a numerical methods basically refers to the behavior of error, right? How far from the true, right? How far from the true when t tends to infinity, right? So we want to exactly the result of our numerical method to exactly match with the true result, right? Sometimes probably some student, how do we know true, right? But in some cases we know, right? Means when we are testing, when we are developing, but when in real system we don't know, right? True state. Absolute stability, or also called A stability. Okay, so generally we have x dot is equal to ax, right? And knowing your prior initial conditions, okay, we can calculate actually x dot, right? X basically, right? X dot means delta x we are calculating, right? So new x is x plus delta x. That's your new x, right? And generally, when you have x dot is equal to ax, right? I think most of you should be able to tell me if I ask you whether your system is stable or not. You will say that we just calculate the eigenvalues. So all the eigenvalues, if it falls left side of the 0, then your system is stable. Okay, and if it is a discrete system, then your all the eigenvalues should fall within plus or minus 1 range, right? Then you can say the system. So in linear case, it is the eigenvalues of the coefficients matrix that are important in determining the stability, right? So that's the A matrix we are. In the nonlinear case, we linearize the system, okay, and consider the eigenvalues of the matrix. So it is still there. Means if you have a nonlinear system, you have to, if you are doing some kind of analysis, some kind of development, you have to linearize the system, okay? And if you are applying some kind of classical controls, you have to linearize the system, okay? And then once you have confidence, then you apply that to the, may make some modifications on your calculus algorithm so that it can be valid on the nonlinear system, okay? Another is stiffness. Okay, stiffness system. So stiff system consists of very fast and very slow transient modes. It means it has time constant that are far apart. What does it mean? Right? Generally, they say that microgrid are generally stiff systems. Okay, so where you have eigenvalues are very near to 0. When eigenvalues are near to 0, they are very fast. Okay, the systems are fast. And if you have eigenvalues far from the 0, okay, again on the all has to be negative side, right? Then only system is stable. If it is not stable, then you need to make it stable by doing some kind of control, right? Then you have a minus kx or k, some kind of a minus k, and then you make new a that will be the stable a that you will have. Okay, so now if you have eigenvalues that are very close to zero and very far from the zero, that is considered the stiff system. Okay, so there are some states are going to respond extremely fast, some states are not going to respond fast. Okay, so what we do, so if we use a stable numerical method to solve such a system, we should try to vary the time step. Okay, why we need to vary the time step? For example, after fast transient modes dies away, we can increase the time step to efficiently reduce overall computation time, right? And that is what is exactly happening in the microgrid. When you are doing some kind of power electronics, so those are extremely fast, 10 to the power minus nanoseconds, right? Switching is happening, and then rest of the loads are like aram se, right? Means those loads are dynamical loads, means they don't change it in like 10 to the power minus 9 nanosecond, right? So very important to understand this one, right? If you don't understand your system, then again it's going to take forever. And that is the biggest problem. The biggest problem is that there are no software available to do large scale transient, I would say, okay, large scale transient microgrid simulation. No such software exists. Okay, RTDS, PSK, probably I don't think RTDS also has that kind of. If you want to simulate 100 inverters together, okay, there is no such software at a normal level, means as like smartphone. Now everyone has a smartphone, right? So that kind of, we don't have a smartphone for doing that kind of simulations. Okay, so there are specialized like national labs have those kind of capabilities, but it's just beyond the normal student can access it. Okay, and actually it is needed, means we need so we should be able to implement thousands of inverters and seeing their interactions. Okay, and there are hundreds of manufacturers are coming in for developing their own control for microgrid with inverters. So we need to know that, so that we can find problems and make our system capable of handling larger share of renewables. Numerical accuracy, numerical stability, right? Again, stability we talked about, true and the calculated one, right? Here we have new state, next state, prior state we are using here, and also the derivative of that, means fx, right? That we are using to do that. Again, we have x dot is equal to ax, and if it's a, means eigenvalues of a is less than 0, system is stable, right? Couple of methods, Euler methods, and forward Euler, you calculate your current values from the prior values. Okay, so prior value of x and the fx, means the derivative, right? This one, and the time step you are using to calculate the new state, basically. So forward Euler. In the backward Euler, you have very similar, right? So this one is, but you are using the current same values. So in this case, you have to do some kind of additional work to get the values, right? You have to internal simulations you have to do to get this current value, to get that xn. Okay, so forward Euler, backward Euler. Okay, forward Euler method is explicit, one step and self-starting, and build upon the previous calculated values, right? First x1 from forward Euler is very unlikely to match with actual x1, right? We can definitely say, right? It's not going to match. Okay, and especially if you don't know the initial condition, right? So it's not going to match. The error from that, right? The error that occurs in a single step only as a result of the numerical formula is referred to as the local truncation error or discretization error. Okay, local truncation error and discretization error. This truncation error can be examined using Taylor's theorem. Okay, that is this, right? So h x dot h square x double dot then h cube and then h n x n derivative of n times of your function. Okay, so hence forward Euler method is of first order and its accuracy is low. Okay, forward Euler stability analysis reveals that it is not an astable method. So forward Euler is not an astable method. Extra care is required to apply this method to stiff system. Okay, generally we will not use it. Okay, at least we should know that. Backward Euler method is one step, first order, implicit, and it requires to solve xn iteratively. So you have to do iterative because you don't know the xn, okay, and you want to use it to calculate xn. So the accuracy is same as forward Euler method, but this method is astable. Okay, hence it is suitable for stiff system. Okay. Simple example you can implement if you like on your MATLAB. Very simple. Fx is given is equal to 2y minus 1, or f of y is given 2 minus 1, right? So f of t comma y is 2y minus 1. And these are some of the results. So if you want to calculate y1, so you can say y0 is given is 1. And then f of t0, y0, right? So y0, you use the value here. So 2 times 1 minus 1. So that is 2 minus 1 is 1, right? That's what we are getting, okay, here. And then you are adding, right? So 1.1, basically. Delta t, we are multiplying, but delta t is given that what should be the time, right? So 0.1 we are, so that is why we are getting 1.1. Y2, you use previous one and the previous values in f, right? So that is y1 you are using here. So 2 times 1.1 minus 1, right? So that is 2.1 minus 1 times your delta t. You will get the second value, okay? And so on. So now if you see here, you have a t, 0.1, 0.2, 0.3, 0.4, okay? And then if you have a delta different, right? So your time step, right? If you use 0.1, you are getting this result. If you are using delta t 0.05, you are getting this result. If your delta t is 0.025, this result. Now, probably some of you may be thinking, which one is right? Right? If I ask you, which one is right, right? Challenging question, right? But no, all are right, right? If all are right means if for 0.1, these are the results you are going to get. That's the method it is, right? So, but we know that when we go, our time step goes slower and slow means time step is smaller and smaller, we get better and better, and then it requires more time to calculate it, okay? But then later we'll discuss that it's not the case. Even that is not the case, right? And probably this is a good example. And if you want to, if you have a MATLAB access, you can just write in 5 minutes, you can write this, okay? So same example, we are implementing, we are saying this system is y of t, okay, as in the MATLAB, ODE difference of y comma t, which is equal to 2y minus 1, right? So that is 2y, this is exactly we are implementing, very simple, okay? Condition, initial condition y of 0 equal to 1, okay? And then y solution of t is equal to d solve ODE comma condition. So initial condition we are giving, okay? So this is the true solution, analytical solution we are saying, okay? That's a true solution, okay? Now if we are using forward Euler method to implement it, what we just discussed, right? So 120 samples, if you do dt is equal to and then you are choosing dt is equal to 0.001, okay? And then you are calculating. So initially y of 1 is y of 0, but we don't have y of 0 in MATLAB, right? And then here we are using it as a condition. So we don't have y of 0. So y of 1 is equal to 1. So this is kind of y of 0. And then if you are implementing. And if you plot it, you can see here. Okay, so that's the difference between analytical solution, right? So we are far from the true, right? It means whether it is acceptable or not, it depends on what you are looking for. But definitely you can try changing the dt, right? Because this is true, is trying to optimize, right? ODE, trying to go as small as possible to solve that time step. So if you probably change this dt, it may happen that you will exactly match these true solutions. Okay. So when we are doing simulations, we don't know what is our true solution and what should be our step size, right? Simulation step size. Okay. Trapezoidal, I think I think new MATLAB has a trapezoidal method. Yeah, earlier they were using some Rangekutta and so many other methods 5 years back, but now I think they saw the advantage of trapezoidal method. Okay, so this is your function. Okay, and then you are calculating the current time step from the previous, and also you are using this one, right? So you are doing the derivatives of the function at the same what you are calculating. So again, you need an iterative method here. Okay, so this trapezoidal method is astable, numerical oscillations as differentiator, solving yn, right? Yn is f of this given previous condition. So we have this one, yn is equal to this, xn again same time step. Okay, and we don't know the value. We need to do some kind of iteration or some kind of modifications in this one so that we can get the current time step. I think we probably have an example on this one. So trapezoidal rule with damping. Okay, we'll talk about it, the importance of this alpha here. Okay, to probably see how we can use alpha, because when you are doing this kind of simulations, you will see some kind of oscillations, right? Here also see very small oscillations you can see. It's not like clear cut like this true solution, right? On this one, similar things that you can observe and that you can help. This alpha can help to minimize that. Okay. The trapezoidal method is one step. Second order, astable and implicit. Okay, so many advantages. One step, second order, astable and implicit. Local truncation is on the order of 3. Okay, and global truncation is order of 2. Okay, hence it is widely used. Okay, if you want to do a lot of detailed understanding of this one, I have added a link here. A lot of small examples. It's good if you are involved with some kind of simulation, building your own methods on your simulations. I think good way. But if you are using MATLAB simulating, probably not needed. But you can definitely spend 15-20 minutes just understanding the details, what is happening if you are using trapezoidal in your simulation. Okay. Okay, so very simple, same example, y dash is equal to 4y minus t. Okay, so if you apply the trapezoidal rule, this is the trapezoidal rule to solve this one. Okay, remember, if we just say differentiation ODE, like what we did here, right? Solve ODE and then the ordinary differential equation with initial condition, then it will solve it, right? But that is generally not the case. So then we need trapezoidal rules. Where is my trapezoidal rule? Sorry, I think I came very fast. Okay, here. So then this is the trapezoidal rule. So we have yn plus 1. We are calculating from previous plus the this step size. Okay, simulation time, right? Step size delta t by 2. F of tn yn is this value. Okay, this y dash is considered f, this one. Okay, and this one is also y dash, but this is at the value of n plus 1. Okay, at this time, right? At this time. So now, if you see here, what is happening? So we have no change here, no change here. So we are putting f tn yn, that is exactly same value here at n, right? Previous time step. For previous value of this yn, 4yn minus tn, previous time step here. And instead of t, this one, so we are replacing t to tn plus 1 and y to yn plus 1 here. So 4yn plus 1 minus tn plus 1 here. And then we are doing a little bit more simplification where you will have now yn plus 1 here. Okay, so you will move that yn plus 1 here. So now you will have this kind of similar solution here. And yn plus 1 and tn plus 1 and tn will become minus, right? Minus delta t basically. And that is why delta tn plus we are going to get here delta t here. 2 delta t is coming from here. 1 minus 2 delta t. And then we have yn delta t by 2 4, and we know that next time, right? Because we know the delta t, that is why we know this one. So all here, everything is known except this value. So we should be able to calculate. So we can write this basically. So reformulated with our work, we have the trapezoidal rule, and now we are ready to do the simulation basically, okay? How that look like. Same differential equation, solve it. And now here we are saying our time step is 0.001, and then we are solving here. So again, this is the true solution or analytical solution, and this is from the one. So trapezoidal method with time step 0.00 second versus actual solution with time step 0.833 milliseconds. Okay, so that's what we are doing. So when you are doing y solve, you are going to get this kind of, I think I forgot to mention, you will get this solution, and then you are using this solution time t, right? And then doing the simulation. So we did the same thing. So when you y solve here, this one, you are going to get this answer basically, okay? And then the answer of this one is this half e raised to 2t plus half, right? And then you are solving it for this one. So this one we are solving it so this is our time step from 0 to 0.1, okay? And then time step is 0.833 times 0.001, okay? Similarly here, so now again you can test it, right? If you want to test what will happen if I decrease this delta t, okay? My guess is that you eventually will reach this analytical solution, okay? If you are implementing your trapezoidal correctly, it is very well, I believe that you should be able to get it. It's very easy to do it, right? You can, like 5 minutes, probably some of you may be already doing it. So you should be able to check with that delta t and see what is happening, how small you can go, okay, and how large you can go, right? Just giving you the flavor of trapezoidal and very simple system, right? F dot is equal to 4y minus t. Range K method, right? Range K method. Let's say not say KUTTA, okay? Range KUTTA method. So we have this one. So probably you can laugh a little bit, okay? That's okay. So we have this one, very simple, fourth order. This is called fourth order. If you use K1 and K2, second order, okay? Just K1 first order. So you have 1 to 4th order Range K method, okay? So K1 is Fx, that is exactly same value. K2 is F xn plus K1 by 2h tn plus h by 2. So it is using K1. In K3, you are using K3. So previously, I think MATLAB couple of years back, it was using this method a lot, okay? So Range K method is one step, fourth order, explicit and very accurate, okay? That is the reason MATLAB was using. Local truncation error was on order of fourth, right? Our local truncation error was 3, right? So this one is, you can say, the third order up to error, and this one is much better if you think of that one. So that was the reason MATLAB was using, okay? So this method is time consuming, but right, it is very small region of stability. It is conditionally stable and not suitable for stiff system, as it requires very small time step, okay? Conditionally stable is not stable, basically. Not suitable for system, definitely. It's not suitable for microgrid system, okay? Okay, Simpson's rule, again, very simple. Next time step calculations, next state calculation, next time step, K1, K2, K3, K1, K2, K3 here. It is the third order RK method, basically. Simpson's rule is third order RK method, Range K method, okay? Simpson's rule is an explicit and pretty accurate. This method is not stable, okay? Then Gear's second order method we have, all right? Again, you should be now able to understand what is it, right? Means what is xn, what is fn, what is h, time step, right? This one is. So you should be able to calculate the next value of your state variable, right? At next time instant. Gears take a second order method is multi-step, implicit, and stiffly stable. Still not stable on this one. Okay. X dot is equal to fxt and x dot is equal to y. Okay. So then two ways you can solve this one, right? One is if you do the integration of y, you can get x, right? Or if you take the differentiation of x, you can get the y, right? So depend what what is your equation, whether you are trying to solve y, you are trying to solve x, right? And if it is x, this will be your kind of a numerical method solution, this one. Okay, and this one, if it is y, this will be your numerical method solution. So integrator or differentiator. Okay, if differentiator, you will have this. If it is integrator, and then you will have h by 2, here 2 by h. Okay, integrator, this, differentiator, this. Okay, solution. Integration and pure differentiation. Okay, so we have different methods here. Trapezoidal integration, xn previous plus h by 2, yn plus yn minus 1. Okay, differentiation 2 by h. Instead of calculating x, you are calculating y, and different methods. Okay, for simple different. Trapezoidal with damping, right? Alpha is very important part. Okay, if you are involved and with some practical aspects, practical system you are solving, it's good idea to consider F. Okay, not academics. Academics is fine, but in the industry, like if you are working in R&D, okay, some kind of ABB or G, General Electric, or any, in fact, R&D work, or Bhabha Atomic Research Center, anywhere, right? A difference equation for an inductance. If you have inductor, current is flowing I in that inductor. What is the voltage? And inductor value is L. So every single student should be able to tell me, right? V is equal to L di by dt. Very simple. Every power engineer should be able to say that L di by dt. Okay. So this is our classical now applications of that. Okay. So we are applying trapezoidal on this one. So here, this is differentiation, right? So that is I of t minus I t minus delta t, that is h by 2L, right? That's what we are doing here. That's exactly what here, right? This is exactly what we are doing here. So x minus xn minus 1, right? So that is, sorry, where is my, yeah, right? X minus xn minus 1 integration 1, okay? This one, h by 2, right? Where is h by 2? Yeah, that's the one, okay? That's the one. So I of t minus, so we are taking dt here, integrating this one. This is what we are going to get in the trapezoidal. So that's how we are going to solve for the currents, knowing the voltage. Okay, knowing the voltage, you will solve for the current. So I of t will be equal to I of t minus delta t plus delta t by 2h, V of t plus delta t by 2h, 2L, V of t minus delta t. Okay. And similarly for all other methods, okay, with damping. So instead of just use delta t over 2L, you will have some kind of damping, 1 plus L, 1 minus 1 plus alpha, 1 minus alpha. Okay. Discrete time transfer functions, HS and VS, right? You have this one, and then you can convert that to this kind of continuous, convert to this one, VZ and this one, right? So this is a classical one. Transfer functions, right? This one is discrete, okay? Poles and zeros for different methods here. And understanding, and now we are saying that, sorry, we are saying HS over HZ, we are, okay, so amplitude we are comparing here. HZ over HS, magnitude or ratio we are comparing with alpha 0.5 pink. Ideally, we want that no matter what your this 1 over delta t, you want that it should stay very near to your 1, okay? But that is when your this frequency changes, your results changes, okay? But still it's good. Trapezoidal is good, right? It's good here. Simpson in this case also good. In this case, your backward is also good. This one gear is not working better, right? And then black also better than the green one, right? Simpson is going far, this one is going less, right? So you need to analyze this magnitude of ratio for your system, okay? But generally, trapezoidal works wonders basically, okay? And phase now we are comparing, right? So this one is h of z over h of s we are comparing. Again, we are looking for a very straight line here on this one, okay? And probably that black and green is here, right? And I don't see the black, probably the black on top of this red, okay? So this is the working good, trapezoidal is working good, different alpha. Little bit deeper this one, just varying that alpha in the trapezoidal rule, right? Just varying the alpha here, okay? Alpha going from 0 to 1 for this case, where you are just comparing the ratio, magnitude ratio, you are comparing for the discrete and continuous of your system transfer function, basically. Okay, so it's depend what we are looking for. Again, 1 is the ideal one. Okay, so for your system, you need to, if you are really developing some kind of simulations or doing some kind of research, right, that is involved national importance. So these are the things that is important. Okay, the simulation, when you are doing this, you are making sure that you are understanding your model and you are doing everything possible to solve for it, right? So this is kind of helping better, right? So this is, we have to stay near to 1. So for your system, right, magnitude ratio, which alpha is better, that you can simulate it, this one. Similarly here also, right, which alpha is better for the phase, right? So you have this one, and then you may have a conflict between this, right? You are in this one, magnitude is saying alpha is this better, but phase is saying alpha is this better. Then you have to come up with a compromise. Okay, what is more important to you on this one? Okay, again, what is alpha? We are saying we are adding this alpha compared to here, okay, this one. But if you are just academic case, probably I don't think it's worth the efforts, okay, on this one. Okay. Very simple on this one. Let me see if I have it somewhere here. Let's see. Yeah. Give me 1 second. I'm just trying to pull it up. Okay. Okay. So let's see. Let me share this screen. Okay. Just prepare one MATLAB simulation. If you can see this one, very simple. We have a voltage source here. Okay. Peak voltage is 120. Phase shift is 0. Okay. You can have a degree or radian, whatever you want to write. This is the newest version. I think I have 2021. Okay. So MATLAB is constantly changing. So if you don't have it, but you still should be able to simulate it. Resistor value, you have a 3 ohm resistor here, consider. Okay. And then you have inductance, right? Induction in Henry. You can give it in nano, pico, right? Millihenry, those values. You can have a series. Very well, later we'll talk about it, why we need series and parallel on this one. Okay, it's very helpful when you have numerical oscillations. Okay, and now, and then you have a capacitor here, some values of capacitor, right? That is nanofarad, right? 10 nanofarad. And then you have a measurement here, voltage, current measurement, very simple. And then you have a switch here. Okay. And that switch is closing at 0.005 seconds. Okay. And then you have another capacitor in parallel. Then we are creating a fault here. Okay. That is this very small closing resistance and then open conductance. Okay. So we are closing this one, creating a line to ground fault here. And that we are closing at 0.05. Okay. Now, instead of local, you can add the solver here. So see, backward Euler, we talked about a little bit partitioning to trapezoidal, different solver they are using. So they actually removed it. They initially had a Range K, RK method. Okay, so they now realize the importance of trapezoidal rule, right? So in this one, we are saying the sampling time is 1, 2, 3, that is microsecond, right? So we are doing the microsecond simulation here. Okay, non-linear iteration inside, that is 10 maximum we are doing, setting up. Okay, and now if you compare, solve this one, now see what is happening. So if you run this one, let's say run power system, completed, now it's working. Okay, solved. Okay, now, okay, it looks like it's solved. Okay, so now we have first switching at 0.005, second switching, that is a fault, so large current is coming out. So now when you are selecting nanosecond. Okay, so now you see what is happening here, right? You are seeing oscillation. Now, it's really an oscillation is, or is coming because of your method, right? Understanding is very important for the microgrid. We struggle a lot when we implemented microgrid. We have a couple of students worked on microgrid here. So this aspect is very important aspect, okay? Whether it is because of the simulation methods that you are using or because really it is happening in the system, okay? Two different things, right? So just demonstrating here. And now I'm changing that one, okay? So we have, let me see what we had in our, okay, so we had this one, okay, that is 10 to the power minus 4. We did this one 10 to the power minus 6. So this is 10 to the power minus 6. And this is the capacitor voltage. Okay, so let's see what we have here. There is the capacitor voltage hiding somewhere. Okay, that's the capacitor voltage we have here. So this is what we are seeing at 10 to the power minus 6 seconds. Okay, now if we do 10 to the power minus 4, okay, how many zeros? 10 to the power minus 4, right? 3 zeros and 1. So we are applying, not changing anything. We are just saying that you are using trapezoidal. Your step size is now 1e to the power minus 4. Okay, and we are doing this one. Okay, now it's gone, right? So you have first switch is closed at this, right? That is here in your simulation. If you see my cursor here, that's the cursor here, 0.005 seconds, right? And then second switch is closed here, okay? Compared to what we had earlier, okay? Let's do one more time, 6 seconds, right? 3, 4, 5, right? 6, this one is 3, 4, 5, 6. Okay, so you have apply here, this one. Okay, so you can clearly say, right, this is happening because of your simulation algorithms, right? Trapezoidal rule. Now we had 10 to the power 6, and then we have one more, okay? That is 10 to the power minus 9, okay? So now, let's say, where is my 10 to the power 9? So we are considering here, so 6, 7, 8, and 9, okay? So 1, 2, 3, 4, 5, 6, 7, 8, and then 9, okay? So that is 10 to the power 9. 1, 2, 3, 4, 5, 6, 7, 8, right? 9, 10 to the power minus 9. Or I can just write 1e to the power minus 9. Okay, that is much easier. So you can just run the simulation, very simplistic, remember, very complex simulations when you are doing PhD, but this is just the concept, okay? So that is why. And if we have to run it, probably it takes 15 minutes. So that's the microgrid that we have, okay? See, 10 to the power minus 9 is taking some time, okay? So I don't think we will be able to do it. It takes a lot of time, but I think I have results here. Okay, I already did it, 10 to the power minus 9. You see one spike you are getting, okay? Now this spike, is it because of the simulation or is it really your system is seeing the spike? Right? No one can answer it, right? But when you do a lot of study, lot of simulations, then you can understand what is happening, okay? You can tell from the simulation is not because of the system. This is because of the method that we are using, right? Because here less spike, right? Here compared to this one, larger spike we are. This is even going beyond this one. And here no spike at all, right? So you can say for this system, 1e to the power minus 4 is probably better time step, right? 10 to the power minus 4 is better time step. Okay, so I think it's a good time to take a break here, okay? So then we will continue a little bit on this one, resistive companion form method, and see if we can finish it and do a little bit more on this one, okay? So let's take a break, maybe 10 minutes break, and then we'll come back. So whatever time you have, just add that 10 minutes and let's talk more about it, okay? Thank you. Okay, we will start in 2 minutes. Okay. Just quickly sharing one thing. If you see the screen, I have a response for the MATLAB. We have MATLAB. Many students has 19, 20, 22. I don't know about 2019. I'm sure that what I'm planning to present. You have the availability. 2020, you have the availability 22, but older version, I don't know. Okay, so probably I don't know whether you will be able to get benefit or not, but at least you can learn, right? You know that new capabilities of the MATLAB. Okay. Okay, then let's work on a little bit of resistive companion method, maybe half an hour or so, and then I will discuss half an hour. Okay. Actually, I should have given you that 10-minute homework before I started this one, but that's okay. To download MatPower or something. If you think your machine is slow, I think it's a good idea that you should download MatPower. Okay, so let me just go back again, share screen here. Sorry. Download MatPower here. Soon that you won't be able to, in 10 years from now, you won't be able to see the source code. That's my guess. Okay, so you can download the latest version here. Okay? Released on October 8. This one, 31 megabytes. Okay, and download and unzip it. Okay, and then we will work on it maybe half an hour from now. See? Okay, so probably if I open my simulation results, probably I will see something like this. So you can clearly say that these oscillations you are seeing like large peak this because of the simulation, right? The method, simulation method, not because of the system, right? You're not creating system. So in real life, when you are implementing this system, you are not going to see that. But how you can tell, right? Very important. So understanding, but once you have this understanding, then you can change the time step and see what is happening, right? So very important part. And microgrid is extremely important part. So next is resistive companion modeling. Very simple is I equal to GV minus B. That's the modeling aspects. So that's the equation. Okay, probably you might have learned this one a little bit. At least I equal to GV we know because V is equal to Y I, right? YI. No, sorry, IR, and then 1 over R is G, right? So that is I is equal to GV. That's what it is. Let's start with simple resistor model. Okay, very simple resistor model here. So you have current I0 and current I1. What is relationship between I0 and I1? Every single student Okay, every single student, if you can't tell me this one, and something is really, really that needs to be seen, right? You can say I0 and I1 both are same, except they are opposite to each other, right? So either you can say I0 is minus I1 or I1 is minus I0, same, right? And then you can have the equation I0 is equal to V0 minus V1 times 1 over R, right? That's the equation. Very simple modeling here. So current I0 is equal to 1 over R V0 minus V1. That's what we are doing here. So we can write I1 is equal to minus I0. So that is minus 1 over R V0 plus, means, right? Or bracket V0 minus V1. So we got two nodes currents, right? One is I0, one is I1. Okay. So external load, this is when we are seeing in the MATLAB, right? So you have a resistor here. MATLAB doesn't do resistive companion modeling. Okay. So this one is where the software is using this resistive companion modeling. So this is how it is modeled. V0, V1, both voltages, I0 and I1, both currents. Okay. And then G is showing the values of the resistor. So for resistor, your I of t is equal to, so you have in I of t, you have I0 and I1, two equations, right? So they have these two equations, I0, I1, and then your matrix that you are going to get, G matrix is G minus G minus G plus G, right? So that's your matrix. That is G means 1 over R minus G minus 1 over R minus 1 over R and 1 over R. And then history, we call it history. There is no, so resistor doesn't store anything. So it doesn't have history. So immediate consumption, whatever goes through it, P is equal to I square I, right? Immediate consumption. So there is no history, no voltage or no current stored. So there's a history, that is B of T minus H. That's the model, right? Resistive companion model. So there is history vector is 0 here. So the model for the resistor is simple, right? Similarly, so this is the model for the resistor, companion for model for the resistor. And then after running my MATLAB, my computer got a little bit slower. Okay. So I'm coming. Let me close that simulation. Is still that simulation is running. Okay. So let me just see if I can stop it. Okay. So that is why. Okay. If I stop the simulation, probably that will resolve this issue. Okay. Inductors, very simplistic, okay, very basic. Then we can go to the larger model, right? Once we understand smaller model, right? Inductor, what we can write is inductor is L di by dt is equal to V. What is the V? V is V0 minus V1. So V0 minus V1 is equal to L di by dt, right? And similarly for I1, you can write. So V0 minus V1 equal to L di by dt, but minus di by dt, right? No, sorry, di1 by dt, but the relationship between I1 and I0 minus, right? This one. So now we are doing integration of this one, dt is integration, and L di by dt integration here. So now we can apply the trapezoidal here, trapezoidal method that we just discussed, right? To solve this one, h by 8, h by 2, v0 of t minus v1 of t plus h by, because we have the limit t minus h to t, right? So h by 2, v0 t minus h minus v1 t minus h. What is h? H is the time step. Okay, remember it's always discrete, right? Though we say continuous, is equal to L, and this one di, that is I0, and then you have limit t minus h. So I0 minus, this would be I0 here, okay, not I1. So I0 of t minus I0 of t minus 1. I don't think I can change that right now. Okay. Little bit more simplification. So now we are solving for current I0. Okay, so we are just saying I0, that is only I0 here we have, and then we have 1 over L, right? And then we have minus I1. So we got this one, L divided here. So h by 2L, h by 2L here. And then we have this minus I1, it will become plus I1 here, right? So we will have plus I1 here. Okay, and then some kind of h by 2L here, h by 2L, right? And then, so h by 2L is not multiplied. That's what I was thinking. That is, h by 2L is just multiplied to this voltages and not to I0. Okay. So this is I0. I0 is coming here, positive. we are taking minus, so that is minus I0. Okay. So in this, so now this is our model for the inductor. Okay. So I0 and then I1 is minus. So that is minus H by 2L, this one, and minus. We are keeping minus here, but we are taking that minus sign to inside here. So we have two currents, I0 and I1. So that is I vector. Okay. And then voltages, we have V0 and V1, and then history. So this one is B in the model that we have here, right? So B1 T minus and H, and B2 T minus H here. So this one is B1 T minus H and B2 T minus H. Okay. And you can either represent that like this. So that is I0 plus B0, right? So that is, if you can think about, this one is plus, right? If you take whole this side on the right, so I0 plus is equal to this. Okay, that's what we are representing. So you can represent this inductor as a resistor in parallel with the current source, known current source. So you can model this one, okay, like this. So I0 is equal to, and this one is B0 T minus H. And if we put minus, if we take minus inside and we put plus here, okay, then we can put the direction of this one downward. Okay, so then we come, because when you have plus here, if you bring it to the left side, it will be minus, and then you will have minus, means it's going away from this I0 nodes. Okay, so again, modeling of this inductor, and then the matrix here, I is equal to H by 2, right? So you will have H by 2 minus H by 2L, sorry, H by 2L minus H by 2L minus H by 2L, and minus minus plus, that is your G matrix, right? And the B is B0 and then minus B0, right? So that is B0 and then minus B0, because we have a minus, I1 is minus, right? So that is minus B0. Okay. So you got everything, and then V vector here, V is V0 and V1 here on this one. Okay. Similarly, for the capacitor, we have I0 is equal to C dV by dt for the capacitor, right? And then when we are integrating here, T minus 1 to T minus H to T, here, both side integrating, here we can apply trapezoidal. Here we don't need to, because the solution here is VC, and we have just a time, just a limit we will be applying. But here, I0 of T dt, the solution is H by 2. So trapezoidal rule we are applying to get the solution from here. That is H by 2 I0 T plus I0 T minus H, right? Only one I0 we have here. What we are solving for? We are solving for I0, right? Knowing the voltages. So I0 is equal to TC, 2C, right? So 2C divided by H, VC minus, you have all the history values here. Similarly, I1 minus, then you can have your G matrix here. You can also model the capacitor with resistor in series with the current source. You can model it. So that's your equation for a resistive companion form model for the capacitor, right? And this is your G matrix, G and B matrix here. Okay. This G and B matrix, okay. And then we can put it. So if you want to use another method, then your value history vector will change. Your G value will also change, because it depends on what you are using it, right? Here we are using in trapezoidal method, right? If you use gear method, Simpson method, it's going to change this value, right? So different methods. So trapezoidal, Ural, and gear. Okay, generally I ask students to go and simulate this one. Use MATLAB or whatever you want to use, and compare the results. Okay, this one. Okay, simply here, this is a boost converter state space model, right? So without trapezoidal, so you have a boost converter, two states when your switch is closed and when your switch is open. So if this is switch is open, right, then you have this and this two scenarios, right? So you can write DIL by dt is equal to 1 over L Vs, right? That's current into the inductor, okay, and current through the capacitor, right? That is dVc. So C dVc by dt is equal to 1 over, that is equal to minus 1 over CRL times VL, right? So you have two states, dx1 by dt, 1 over LU, that is input, U is Vs here, and the second state is dx2 by dt minus 1 over CRL x2, right? That is, and x2 is IC here, probably. So x2 is IC here, okay? X2 is IC. and x1 is IL here, right? And x2 is VC, sorry, x2 is VC here. Okay, so VC your state variable, IL is your state variable here. So you have x dot. So how you are building your state space model here, dIL by dt, that is x1 dot and x2 dot here, right? Nothing in A matrix because directly you have is the input, right? So input is 1 over L Vs, and then on the second row of your x2 is equal to nothing x1, so 0 minus 1 over x. So this is your state space model for one state of this book converter. Okay, now again second one where you close this one. Okay, so first one is when it was open here, right? So the switch S1, this diode was basically reverse bias. Right now the diode is forward bias. Okay, second case, you close the switch here. Again, you have the two equations, right? dIL by dt. So two states, you can have another matrix. Okay, now what happened? You have just one boost converter. You have two state space model, right? How you are going to simulate this one if you want to simulate on this one, right? So again, it depends on, right, the switch, when it is closed, when it is open. So this guy says that Middlebrooks state space averaging method he came up with. Okay, so when you have this one and you are not worrying about too much about the switching, okay, if you are not investigating, okay, then you can take advantage of this method. If you are not worrying about the switching, right, you are just taking the average. So he says that if you have x dot and x dot, both are the same state, but your system is different in both cases, then you can have the average model, very valid for the microgrid system. If you are not worrying about the switching, this is a good thing for the microgrid system. Okay, again, you have to build all these equations. As a PhD student, definitely is must, but for master, probably you may not go into a lot of development here. Okay, but again, it depends on your ability, right? How much you can understand, how much you can apply. So this is average, and it's saying that A matrix for the average is A1 times D, what time the duty cycle, basically, right? This one you are closing, or I think I'm here when we are saying is, sorry, what happened here? I think this is the switch we are talking about, right? So this switch is closed, and then this switch is open. This will be automatically in the forward bias if this switch. So we are talking about duty cycle here. Okay, duty. So if this switch is closed, this is reverse bias, and if this switch is open, then this is forward bias, right? And then you will have this second state here. So I think probably I misspoke there a little bit. Okay, but it's still the same thing, right? S1, whether forward bias or reverse bias. So not 100% incorrect that. So then you have now your average model of the books converter looks like this one. Okay, so nothing to do at this stage, nothing to do with the resistive companion model. Okay, so if you also just simulate a boost converter, this is your model. If you know your D, you should be able to get your states, right? State space model of the boost converter here. Well, now for the resistive companion model, okay, so we are saying the switch is closed. Okay, so we have just because when we are doing modeling of the boost, we don't model the source, we are modeling the input output, right? What is inside your boost converter, output, whatever you are connected. So if you are modeling this for your simulation, right, and so whatever you are connected here, load, or whatever the source you are connected, or source side of it, so we are just modeling this part of the boost converter, right? Just L and C and the switching part. So when the switch is closed, this is closed, for diode is reverse bias, and you will have a model like this for the boost converter, right? And then you have di0 by dt, that is equal to 1 over L, V0 minus V1, right? And then similarly for the voltage, V2 minus V1, right? We are calling this is V2, V2 minus V1 is VC. So dVC by dt, C dV by dt is I, right? That's the current we are calling. And then you can have two current for this one, two current for this one, right? So that is 4 equations. So I0 and I1 is minus, and this one is I2 and I1 is minus, right? So you will have 4 equations out of it. Okay, so 4 equations for the on state, and then you have 4 equations for the off state. Now when it is off, This is forward bias, and you will have system like this, right? So your I0 will be equal to 1 over L, V0 minus V2 now. Okay, it's no longer just what we had earlier, right? So V0 minus V2, the current here. Similarly, V2 minus, so C dV by dt is whatever the current here. So now the current here is I0 plus I2 that we are modeling here. Okay, it's a little bit involved, okay, but it's understandable. I think every master's and PhD students should be able to understand this one, right? So dV2 minus V, right? So you will have this one. So similarly for minus, right? So that is, you will have here, this is I1 current only we are going to have. So I0 plus I2 is equal to minus I1 if you are saying, right? I0 plus I2. So you have minus here and then here I0. So I0 is now no longer minus I1, right? I0 is no longer. So here you have to come up with the current, right? So that is I2 current probably. I2, even the I2 is not minus current, okay? So you have to be careful about that. So Middlebrook, again, two states, right? On state and off state. You can add them up. You can have these equations, right? D and 1 minus D, D and 1 minus D. So both states, your states are not changing, right? Both cases. This one. So we are identifying the terminals for this one. We have 1, 2 terminal, two terminals here. Okay, and now we are ready to apply the trapezoidal here. Okay, let's see if we have done it or not here. So we have this RCF model, that is I is equal to GV minus B. So you can build a boost converter model as a RCF model here. Okay, so this is di0 by dt. You do a little bit of math, right? So we already explained to resistor, inductor, and capacitor. So, and then you can come up with your I0, okay? That is following the steps size, right? Time step of your simulation here. You have B0, where B0 is this, okay? Complex, lot of work goes into it, okay? To come up with this, almost you should be spending like advanced PhD student probably half an hour, master student probably a couple of hours before you really come up with the right equations here, okay? But I'm just presenting quickly here, okay? And similarly for second equation, right? We have two equations here, di0 and dv2, right? So second equation here, and then you can get that I2 and B2 is this, okay? Very complex if you have to do. But again, we are doing, this is the heart of that model, right? That's what goes into the model. When we are taking it for granted, we just simulated a simple circuit, right? I just pulled back some component, put together, switch and everything. But behind, somebody is working very hard so that we can do that simulation, okay? So that's the hard work here we are showing. Now, this is a complete G matrix for the boost converter, right? Again, this one is 4 nodes, so 4 by 4. And then you have, this one is 3. And then I think we are not showing, right? So BET of this one, sorry, 3, right? So we are saying we have 3 values, 1, 2, and 3. Yeah, so we have 3 values here. So that is your RCF model for the boost converter, okay? Simple, I think, probably 15 more minutes we will talk, and then we'll jump on to the things that I was mentioning. Okay, hope you have already downloaded that MetPower. Okay, simple. Now we have the source here, we have the model resistor, and then we have a capacitor here. Okay, and we want to do the simulations. Okay, so we are saying that this source is model. We can convert this source transformation, right? If voltage and resistors connected in series, you can transform them to current and resistor in parallel, right? Probably you learned in your BS, bachelor degree, BTech or BE, right? So the same resistor here, capacitor, we are modeling with resistor and in the current source, okay? We are saying that time step, we are choosing 0.1 second. Initial voltage of the capacitor is 1 volt. And we want to solve this circuit using RCF model, okay? That's what we are trying to do. Your G matrix for the RCF system, you will obtain this one, 4 minus 2 minus 2 and 12 T2. You have the B of history. We have only one history, right? That is the capacitor, because it's storing the voltage, right? So that's B. B is this values if you calculate this one, okay? And then here are the results, okay? So step 1, At step 1, current time simulation is t equal to 0. Previous time is t is equal to minus h. Okay, then we can write b of t minus h, right? So that is this value b of t minus h. T is 0, right? So t is 0 and h is h, right? And then we have IC of t minus h. So we are putting t equal to 0 here, plus 2c by h VC t minus h. So we are putting t here. So VC, we know that is 0, right? So we are getting this one is VC of minus h. Initial voltage given to us is 20. Okay. And if you do 0.1 here, and what is the value of capacitor given to us? Capacitor value is 1. So that will go away here. All right. And then we are going to get 20 values here. So B of previous B of minus h, basically we know is 20 value. So V of t equal to 0, V1 we are solving for voltage, V1 t equal to 0, G inverse B. Okay. This is our model. This is what we are solving for, right? B is this 20 and B. So we got this one, and then we got these are the voltage at t equal to 0. These are the voltages. Okay. At step 2, current time t equal to h now. Previous time is t equal to 0. Now we are calculating. We need this IC t minus h. Okay, so we are first calculating IC t minus h. T equal to h. So t IC is 0 here, which is equal to 2c by h VC t minus h, that is h minus h is 0 minus b t minus h. Okay, so that is minus h. We are going here, right? We are going, let's see if I can understand that one. So we are doing here the I equation, current equation. Okay, we don't have this one, but B of t minus h. So when we are doing t minus h simulation, we are going to have here t is t minus h. So we are going to have 0 minus 2h, basically we are going to have. That is exactly what is happening here. So that is why 0 minus h we are getting here. We already have 0 minus h, that is 20 here. So we should be able, so all other I of 0, IC of 0 is known, VC of 0 is known, and B of minus h is known, and we should be able to calculate IC, that is 8.57. Okay. Once we know IC of t minus h, then we can calculate BT. Little bit again complex, okay, here, understanding. But if you probably, you have to work on it, okay. Technically, I should give you the quiz, but I think more important that I should show you the capabilities of MATLAB, okay, new capabilities. So B of t minus h, B of 0, right? That is h, current time step is h minus h is 0, B of 0 is equal to IC of 0 plus 2c by h, VC of 0, and you get this value. And you can calculate the new voltage, that is t equal to 0. Now you can calculate your next time step voltage of this, okay, and that is this voltage, okay. So that is time step 1. Then you can follow this one when your 2 time step voltage is next to each other, then probably you can say that my simulation is converged. Or if user said okay 0.1, then you will simulate until 0.1 for this one, okay. So linear circuit solution with RCF model, okay. Now diode, okay, so nonlinear circuit solution with RCF model, okay. So this is nonlinear, right? It's the power is nonlinear, this one. So how we can model this in RCF model? Source, this one, and then we have our diode, so diode current. So you can do KCL at node 1, KCL at node 2, and then diode current is this we are going to get. So I'm going a little bit faster than expected, okay. You can technically I can spend up to 11-15 on these aspects. I really want that you should know the new capabilities of this one, okay. And tomorrow we will be discussing microgrid, and then you will do hands-on on OpenDSS. Okay, so we'll be you should be able to model some 3-phase distribution system tomorrow. Okay. Okay, so we got this one. So ID is this. So when you have nonlinear, you need additional iteration, like I showed you on MATLAB that we in that selections, so settings of the simulation, We had time step and then nonlinear simulation steps also. 10 we selected. So that exactly we have to do here. For every time step, we have to additionally solve that a nonlinear part of it. Okay, so whenever you have a nonlinear part, you solve it, you do iterations for that one on that one. Okay. Okay, let's see what it is saying. These equations are nonlinear and need to be solved by iterative method, Newton-Raphson's linearization procedure. Assume V1 and V2n are the approximations of the node voltages at the nth Newton's iterations. Goal, solve the circuit at next Newton step, n plus 1. That is our goal. Okay. Diode current at n plus 1 step can be expressed by first order Taylor series. So we are now putting the Taylor series expansion on this one. So how far you can go, right? You can go up to whatever you can think of, right? One derivative, two derivative, three derivative. So, okay, so the nodal equations at n plus 1 at Newton steps will become this, okay, and at node 2 will become this, okay. So above linearized nodal equations can be solved by LU defactorization, right? LU factorization, LUF, to determine the new approximations of V1 and V2 at the n plus 1th step. This procedure is repeated until the change in the best approximation values for this voltages between iteration step is acceptably small. Circuit solution is converged, right? So very important that nonlinear part, you have to do Newton-Raphson's to solve it. You solve it, come back here, and then again solve it for your time step. And then we can say that it is converged. Now let us revisit the above nodal equations. So we have this nodal equation, node equations 2, okay, nonlinear. And this is where we are doing, see, Jacobian is coming in here. Okay, so GD, we are calling this one is GD, right? GDN. So BDN is GV minus I, we are calling. So partial derivative of ID is now we are representing F, V2, and then Newton n step, we are doing iteratively solve this one and then putting that solutions here to calculate the solutions at the current time step, okay, or next time step. Very important. So nodal equations becomes node 1, node 2 here. So in GDN, V2n, and BDN here. So these are the nodal equations, okay, of linear circuit at n plus 1/8 Newton steps. And GD is non-linear. Please note that one. GD is this, e to the power. And we have to use some kind of iterative method to solve. Newton-Raphson is one of the method that is widely used and very well accepted in our power community. Okay. Okay. So the RCF model for this one is we can write Ij n plus 1 GD minus GDN, right? So we can see RCF models we are, and then BD, right? So BD, GD. So we have in the GD itself now we have a non-linearity here, okay? But we can model it there. And whenever the voltages are known for this model, we come back here, internal solutions, nonlinear solution, Newton-Raphson, and then provide the currents, okay, to this one. Basically, we calculate the current, that how much current this model diode is going to take. Okay. Okay. I think I'm going a little bit fast. We have a couple of more slides. Okay. So comment, although this discussion of the nonlinear circuit modeling and simulation procedure has been presented for a simple example. I don't think it is simple, but let's say simple example because it's just a one diode. Okay. So when you are doing some kind of simulation, you have multiple. The same fundamental principle apply to any more complex nonlinear circuit. Note that the above discussions is for steady state or DC analysis of the nonlinear circuit without any involvement of time. It means if there is no time stepping, if the circuit has dynamic devices such as inductor or with time varying elements, we need to perform the above DC analysis at each time as we march from time step to this. Okay, very important. Okay, so now the larger one. Okay, so quickly. This one DC machine, how we can model DC machine, RCF model. Okay, so we have a terminal G0, 1, 2. Okay, and 2 is I think torque probably. Okay, so external. So step 1 for any machines or any model, step 1, identify the terminal. So we are identifying terminal. Step 2, identify through and across variable. Through is current, across are voltages. Okay. Step 3, get device differential equations basically. Step 4, apply appropriate numerical integration, generally trapezoidal or gears method, and then get the model of this is general steps to obtain the RCF model. Okay. So basically knowing this, you can build your own simulation engine. Okay. If you are keen, you can build it, but require a lot of time. Okay. This one. Well, I think simply one person cannot do it. Okay. One person cannot do it in reasonable time. Okay. Let me add that one. So identify through. So for terminal 1, through variables I0, across variable is V0. Okay. Terminal 1, I1 and V1, and terminal 2, torque and W here. Okay. Frequency probably or speed. These are the nonlinear equations. Any book should give you these equations. Okay. Differential equation for nonlinear machine. And then after numerical integration, you get I0, you get B0t minus H. Okay. I2, similarly, after integration, you get I2 of t and B2 of t here. Okay. And if we put everything together, you will have RCF model of machine. Okay. And you can build any RCF model because any circuit in our case can be represented by RLC, right? That is the important why we learn RLC, right? Because you can represent any power model mostly with RCF. A little bit electronics probably you need, but general sense, right? RLC can be a good estimate of any electrical device. Okay. Okay. So I will stop here. Give me like 30 seconds. Okay. And then I will come back and we can start exploring this. By that time, please have ready your Met Power file. Okay. I will also download this one. My case. Okay. Subscribe if you want. Give me 30 seconds. Okay. Maybe 1 minute. Okay. Okay, so I am back. Okay, so let me share my whole screen now. Yeah. Okay. I'm closing my simulation. Simple simulation. We say yes. Okay. So I have a MATLAB. That's my user path MATLAB here. Okay. And then we are doing this mat power. Okay. And that mat power is we got here, right? And then we can just copy this. If you are following with me, I think that would be great. Okay, so you just copy, go to the MATLAB folder here, okay, and then we just copy, paste here. Okay. Anyone is working with me means if someone is working, just send me a chat message so that I know someone is following what I'm doing here, so that I can be slow. Otherwise, I will just because we know that several students had a MATLAB. If anyone is following, please just write a chat message here. Okay. Okay, very good, Swati, very good. So now, if you have put your, if you have selected this, right? Okay. If you have selected, if your path here is MATLAB, right? And if you have MATLAB here, so you just right click here. Okay, and then add path, says selected folders and subfolders. Okay. Folders and subfolders. Okay. Once you do that, okay, now let's go and design some app, right? That would be so cool, right? If you can design an app. So if your MATLAB has an app, then you should be clicking here, design app. Okay. So we'll just close this one. Okay. So design app. Okay. Let's say select blank app. Okay. Simple things we'll be doing here. So anyone open the app? Anyone has opened the app? Please write me on the chat message. Okay, very good. Okay, then what we need to do? Let's do simple one. Let's say this one plot here. Okay. You can do all advanced stuff, but I'm just showing you the basic, and then you can work on advanced stuff here. So we just added here, and you can just expand a little bit here. Okay, so we got voltage here, and then we can say push button here. Okay. Okay. So when you are making this, right? So then MATLAB is automatically creating the code for your app, right? And then that code, then you can export that app to independent MATLAB, and there are several other options are there. Okay, but you can see that one later. Okay, so now I will say run power flow. Okay. You can do all time series analysis, lot of dynamic simulations. Okay, you can change the load value, you can change the generation values, dynamic simulation you can do. So once we have this one, right, run. So I just double click on the name, and then I would change the value there. Okay, you can fancy however color. I'm not doing it, but let's see. Okay, some good color background you can do black. Okay. I like more, okay. But that's not the focus. Focus is that we want. Okay, so call back, right click on this one, call back, add button, push function. Okay, so now when you do that, you have these options here. Okay, Now, because we have already selected Met Power here, okay. So let's go back to Met Power, okay, understand what is happening in the Met Power, okay. Two things. Here Met Power, and let's go to data first, okay. So here Met Power has all kinds of data, okay. Okay, we got it here. So we have 13,000 bus system, okay. But definitely we don't want to touch that right now, but lot can be done, right? Let's go with simple one so that everyone can understand. 6 bus, okay. So if you open this file, you will know that this is the name of the file, and this function basically K6WW, that is WW stands for Wood Woolenberg. That is the author who created this file, okay. This created this system, okay, and also available. This is the book, okay. So MPC, it returns the MPC here, okay. So when we say that here, because it is in our path, we can say MPC is equal to case 6WW. Okay, hopefully it should run, okay. So it ran it, okay. And then in MPC, you can say MPC bus. So MPC dot bus, okay. You can get all these values that you have here on your data file. That is one way, right? So that's the data file you ran. So basically, if you want to run this now 24 hours, right? So a load profile. So you create a load profile, okay, and change this value. How we are going to change this value? Let's say if I want to change this 70 to, let's say 70 is peak value, let's say, okay. And we are in the morning, and probably 0.2 is the so 20%, okay, or 80% less, okay. So 0.8 times 70, okay, and 0.2 times 70, so 14. So let's say we are in the morning, and instead of 70 megawatt, the load is 14 megawatt. How we can change that, right? And PD and QD both. So MPC dot bus, okay. We are saying this is 1, 2, 3, 4, right? Fourth column, right? And then third row, right? Fourth column, and fourth row, third column, right? That is equal to, we are changing that to, first we need to save it, but we are not doing it, okay. For this is times what we are doing, 0.2, okay. So we are changing that value to 70, okay. So now if we say that 14, it should be 14, right? So we have MPC dot bus, fourth row, 3 column, okay. Oh, sorry, fourth row, third column, 14 value, okay. Similarly, you can change the Q value as well, right? So number 4, you can say that is also 4 times 4, okay, times 14. So this is what I am valuing here, is the coefficients of your load curve, okay. That's the coefficients of your load curve, 20, right? So 20%. So now we can check 4, it should also be 14 something, okay. Whatever it was, right? 4, fourth row 4.2, I think, right? So what we did, 0.2, 70 times 0.2. I don't know why we did not get MPC bus fourth row and fourth column, okay. 1, 2, 3. I don't know why we got 2.8. Anyone knows what is happening here? We got 14 here. That is
4,3, sir. You entered 4,3.
Right. Okay. So that's what's wrong. Okay. Thank you. Yeah, sometimes happens. Okay. So 4,4. That's right. Okay. And then thank you very much. Okay. So you got so now whatever we change it. Okay. So we can change it back. MPC bus 4,4 equal to 70 for now. We can bring it back, and then we can just say MPC dot bus 4, times 0.2. Okay, hopefully this should fix it now. We should be able to see 14 value. Okay, thank you very much. Okay, so that's just a flavor. You can change it, right? So that is one thing. And second thing is that we have a library here. And then let's say we can go to see, these are all the algorithms. If you want to debug, understand what is happening in a large scale, right? So that's your file. That's your new fast decoupled load flow implemented here. So you can see you can run smaller 3-bus system and go through every single core so that you can have a deeper understanding of how it is done in energy management system. Okay, but we are just want to use it for now. Newton Raphson's, right? So all the algorithms, OPF, I would highly recommend anyone is master's or PhD student, just do the calculation, hand calculation on very simple 3-bus system and follow, okay? Follow this and understand deeply what is this, okay? Where is our run power flow? Okay, so run power flow, let's see, open. Okay, so run power flow, these are the returns values, okay? And then it needs case and these are options, okay? So let's say, if I say this one, for run power flow, okay, run power flow here, and that is equal to run. Oh, this is not OPF, we are looking for run PF, okay? So run PF, PF is copy. So these are the return values we get. Okay, and then we can say run PF, and then our file case 6, or we can just run. I think we should be able to run because it's let's see if it requires case data or not. Okay, because we had MPC was there, so it just took that values, okay, and it ran it. Okay, so that's a good thing. Okay, so when we are results is already popping up here, but if we see bus here, okay, so let's say bus, because it's written bus. Okay, in the bus, where are our results? Okay, we are looking for some kind of results, voltage results. So these are our these are our bus voltages. Okay, so in the app we just want to plot this bus voltages. Okay, so we want to plot this. Let's see if I can change my preferences so that it's not long sort. We just want sort results. Okay, okay, and then we can just say bus here. So sort is good. Okay, so we get this. So 8th column, right? So 8th column has voltages, and then these are the angles. So 8 columns, so we can just write bus, okay, and all the rows and 8 column, right? Bus and all the rows and 8 columns. So all the voltages we get it here, right? All the voltages, and we want to plot this voltages, okay? Okay, so now let's go back to our app. Okay, so you already have the very basic understanding of this one. Now we want to say that when the button is clicked here, okay, when button is clicked, we want to plot that voltages of this. Okay, so first what we did is we just ran MPC. Sorry, MPC. What was that? I think MPC, right? So MPC case. Okay, so we say MPC case here. Okay. So we can say MPC case. Okay, and then second thing we did here is where is our, how did we run it, right? MV. Let's see what we ran. Okay, that was the run. So we ran the power flow. You see, so we are running the power flow now here. Okay, we got the results. Okay, and let's see if we should be able to run it, right? And so clear all here. Okay, I know everyone has to go for a dinner, okay, or time, but I think we should be, oh, sorry, clear. Back to our app, design, save. Okay. Let's say we say load flow, okay. Okay, Okay, then you can change it and you can make it like a dynamical analysis. Okay, where you can investigate when you change the load, when you change the generation, what will be the line flows and those kind of things. Okay, so this is kind of very basic on that part. So we run this one. Okay, app is there. Okay, so it's not going to show anything in the app, but yeah, by clicking this, we ran the power flow. That's a good thing. That's one step ahead. Okay, now we want to plot it. Okay, let's see if we can plot it. So plot. I don't know the command, but let's see if we can figure it out. App axis. Okay, app axis. We can say app axis. Okay. And then we can say buses. So we have buses 1 to 9 bus, right? So we can say bus. Okay, first column, right? So all the rows, first column, right? That's the bus we are getting. And then we are saying bus, all the rows. And what is the column number? All the voltages that we have. Okay, we remove that one. But let's say, let's run again. Okay, so that we will have, I don't think we will have a bus. Okay, bus not there. Let's run again. Bus. Okay, so that is 8th column, right? So we know that in 8 columns we have voltages, right? So we can say bus 8 column here. Okay, and I hopefully it should plot. Let's say otherwise we'll get an error. Okay, so app axis, what it is doing is it is accessing this portion of your app. Okay, and then X and Y, and then you can do all fancy things here and plotting the voltages. Okay, so let's see if we can run again. Yeah. And let's see if it will show us, and then you can change your X title, Y title, and all these things you can do. So we got the voltage. So it ran the power flow and it gave us the voltage, and you can verify it, what's going on. So remember, every time you do, you just make sure that you are verifying your results, right? Very important. So bus 1, we have 1.0, right? That's the bus 1. Bus 2, 1.025. Okay, so if you click here, 1.025, right? And then bus 3 also 1.025, and bus 9 we have voltage, let's see, 0.996, right? 0.996. So you can do all kinds of very good app you can design it, okay, on this one. Okay, I think we can stop here, and let me take a couple of questions, okay, and then we can meet tomorrow, okay? So I'm open for any questions, okay? I hope you were able to follow this simple new features of app, MATLAB app, okay, for last couple of years. And a lot of things you can do, a lot of things. Okay, you want to see the function. So that's what we did here. Okay, very simple. This one. Yeah, and there are a lot of things you can do here. You can connect to your HTML file. You can put like in RTDS, you have gauges. You can put gauges. You can change, so you can connect now. Basically, I can go here because MPC, I know where is my load, so I can connect that load to my app here, right? And then I can change the load value by either linear gauge, okay, or by knob, okay, or by many other fancy things. Discrete knob, I want to change, right? So different gauges that you can add. So basically you can say here, and you can change the value from here. Let's say maximum value 100, right? So you can change it to change whatever the value, right? You want to say 1,000, right? So you can get 100, 600, 400, 200, okay? And per click, whatever you want, right? So that's your voltage, okay? I think I did not do it good job on that one, but you should be able to figure that out, okay? And then you can select this one, call function, add functions, right? On this one, and then you should be able to change it. Okay, let me bring back this one. So, half gauge. callbacks and new context menu. Okay. Okay, this is the context menu. Where is my knob? Probably we should have a function here. Callback function. So you can add a value, changing value. So continuously, when you are running this one, you are calling your function, executing, seeing what is changing. Okay. So you can basically build a GUI for your control system, basically here. Any deeper control system you can, so you don't need to see any, if you are presenting to your professor, you are presenting to the company somewhere, instead of showing all the details, if you see this one GUI and changing, I think that would be more impressive. Okay, any other? Okay, this one I will just copy and paste here, this one. Okay. So you can have it. Okay, any questions for me? And then tomorrow we'll talk about microgrid, demand response, and then we'll work on hands-on on OpenDSS. Okay, so we'll do one example on OpenDSS, hopefully, quickly. Okay, looks like you all are tired, not ready to ask any questions, so that's okay.
Sir, what is like so special in this? Like why we are plotting in this app? We can also plot directly in the command window. Like
Yes. So we can't do in like if you want to simulate, right? You want to change the load, how you can do it? Multiple load on this one. So this is kind of a GUI for, it will give you kind of a flavor of an energy management system. Okay, you can design SCADA, you can design, if you are, Swati, you are seeing RTDS, right? So in RTDS, you have all these gauges. When you are doing anywhere in control system, you are not just going in the program and changing it, you are changing in outside. So it's just to give you a control app that you can change your program from outside. So
sir, is there anything
design
like agents also here defined? We
so
can
if
use?
I let me see if you have some kind of agents, right? So say that your program is running, your app is running. Okay, so this is your app, and then on the back, so let's say I created a 3 bus system or 6 bus system here. So I plotted here, I plotted all the power flows and all the currents and voltages on this, right? And now I am changing my load dynamically, so it is running every minute simulation, it is running on this one. And then whenever I'm running, so I have the results, right? So and then I'm reading, I'm going here in the code, and then every time it is
The
running, I'm
screen is
jumping.
not visible. Are
Oh,
you doing anything on the screen?
sorry, I stopped the screen share and I was just clicking. Okay, sorry, thank you. This one, okay. This one. Here. Okay, so you are coming here. Okay, so you have the GUI here. I spoke a lot of things here, but you have a GUI here, 6 bus system. You managed to plot it. You managed to put all the values of the power flows, voltages, angle, everything on the screen. Okay, and then you have that system is running continuously, plotting your voltages and all the information. Now, let's say if you want to implement control, right? Secondary control. You have some controller devices. Okay, so you go back here. So you have that one now, all the controllers. So you go back here, write the code to read and write, read from the text file and write to the text file your results. Now you have all the results of PowerFlow here, right? And then you have, and then your agents are running on your Jade platform, right? And then agents are sending, changing those text files, okay, those controls, zeros and ones and whatever those control, right? We saw that agents are, so their agent communication is happening, and the control, the data agents are getting from your GUI, basically from this program, basically, right? Voltage and currents and power. And then if they see the violation, so they here you create a system, right? When there is a violation, your bus voltage, bus line or bus voltage will go to red or something that you can create here. And then that information, now you send it to that text file. Okay. And then once you have that one, then your agent is reading that. Okay. And agent has that information of the system. Agent has the information of the control devices. Now it is changing that control based on whatever you programmed, right? And then it is going to come back and turn on the step-by-step increase of capacitor or SVC or whatever you are modeling, right? And on GUI, you will see that voltage violation is removed. So that is the advantage here. Means a lot of things you can do. Lot of things you can do. I am just giving you one example, but a lot of things can be shown here with MATLAB. Does that help, Swati?
Yes, sir. I'll explore more. Like, I think when I'll work, then I'll get more of it.
Yeah. Means that is always the case, right? Means this is the high level view, but it can be done. That's what I'm saying. So if you, and I think information out there is 3-4 years old. This most of the information you should be able to pull it up. Yeah. But you were right.
But
Means the things that I just showed it. What is the use, right? Means, but I'm just showing it's not the use. I'm just showing the capability that you can run from the GUI and you can do a lot of things from that. Okay.
okay, sir. But thank you, sir, for making us a view, giving us overview of this all.
Very good. Very good. Okay. Any other questions that I can answer on this one? Okay, then we can discuss and we'll meet tomorrow, and tomorrow will be more challenging. Okay, so we'll be doing 3-phase modeling of distribution systems. So very similar to microgrid system, and a lot of things we'll be talking. Okay. Thank you very much. Have a wonderful evening. Have a good time with your family, friends, and enjoy the evening a little bit, and definitely go through the slides that I'll be sending tonight and then review it tomorrow. Okay, so that we can have a small quiz tomorrow. Okay. Thank you very much. Thank you, Dr. Prerna. Thank you, everyone. Thank you, Gyan. Okay, so I'm closing it now. Okay.
Thank you, sir.